300 tons of steel, one locomotive, 3 days, nothing. A machine that hauled 10,000 tons becomes scrap in 72 hours. Wheels that rolled 2 million miles sheared off in one motion. A 20-ton engine ripped from the frame by crane. The diesel tank holding over 1,300 gallons sliced in half in 10 seconds. This isn't an accident. This is scheduled decommissioning. The most precise, cold-blooded, calculated process in global industry. Today we're showing you how locomotives die. Why behind every death lies exact mathematical calculation. And where the metal goes when a train reaches the end of the line. On the edge of an industrial city sits a massive concrete lot the size of an airport. Rows of dead machines stretch beyond the horizon. Diesel locomotives, electric engines, freight cars, tankers, refrigerated units, several hundred strong. Each one's a former workhorse, run into the ground. A TE-10 series locomotive weighs 276 tons. Over 40 years, it traveled more than 4 million kilometers, 100 laps around Earth. A hopper car, 78 tons empty plus 100 tons of cargo every trip. Now they're tapped out. Metals fatigued from constant vibration and temperature swings. Corrosion ate through load-bearing beams. Wheel set bearings hit their limit. Repair cost more than replacement. Economics beat engineering. So the machine gets put in line for total disassembly, down to the last bolt, the last rivet, the last square inch of steel. Stage 1 of recycling is prep, the most dangerous part. A single locomotive's fuel tank holds up to 7 tons of diesel. The lubrication system, half a ton of industrial oil. The cooling circuit, thousands of gallons of antifreeze. Electric locomotives transformers, special dielectric oil that releases toxic fumes when burned. All fluids get pumped out with industrial equipment. Work runs 8 hours straight. Fluids go into separate tanker cars for processing. Diesel gets filtered and sold as industrial fuel. Used oil regenerated to commercial grade. Antifreeze cleaned and back into service. Not a drop wasted. One stray spark, the entire yard goes sky high. Open flames banned, spark-producing tools banned, even regular cell phones banned. Only when the locomotive is bone dry does real teardown begin. First, they strip out whatever can be sold whole. No cutting, no torches, no press. Battery packs, tons of pure lead. Traction motors, pounds of pure copper in the windings, sold as complete units. Power transformers from electric locomotives, copper coils weighing up to 2 tons apiece. Cable harnesses, miles of copper wire, spooled into coils. Instruments, sensors, control computers, all sold as parts to keep working locomotives running. Next, the wheel sets. Alloy steel, hardened to near diamond toughness. One set weighs 2 tons and sells as premium scrap for casting new wheels. Then they pull the cooling radiators, aluminum blocks the size of a small truck, each weighing about a ton. They remove the air compressors and unbolt the high-pressure fuel pumps. Incredibly precise devices machined to within 1/100th of a millimeter. After that, they yank the engine from the frame. The D49 diesel, 20 tons of metal, 4,000 horsepower. An overhead crane lifts it through a roof opening. It's headed either for full overhaul or straight under the press. Now the locomotive's down to a bare steel skeleton. That's when the real monsters come in. Hydraulic shears, the scrapper's main tool. Crushing force up to 1,500 tons. They cut through an 8-inch steel beam like paper. One movement, no sparks, no flame, almost no noise. Where shears won't fit, tight spots, complex welds, they bring in the torch. The oxyacetylene flame heats metal to 3,000 degrees. Steel melts instantly. The cutter, in fireproof suit and dark mask, guides the jet along the seam with surgical precision. Sparks fly 30 feet in every direction. A 100-ton body breaks down in 2 working days. Cab, separate. Frame, separate. Shell, separate. Fuel tank, separate. Engine covers, separate. Every piece gets its own number and goes to its own pile. Metal gets sorted by type, the most critical step. Sorting accuracy directly determines the final price. Ferrous scrap, standard carbon steel. Non-ferrous, copper, aluminum, brass, bronze. Stainless steel, separate pile. Engine block cast iron, separate pile. Alloyed steel from wheel sets, separate pile, worth almost 10 times more than regular steel scrap. Sorted metal gets pressed. A 2,000-ton hydraulic press crushes bent steel sheets into a dense cube about the size of a household fridge. One bale weighs up to 5 tons. Density nearly matches solid steel. Bales get loaded into rail cars, the very same freight cars that will one day end up here themselves, then shipped to the steel mill. There, at 1,600 degrees, steel melts in an electric arc furnace and gets cast into fresh billets. One retired diesel locomotive yields roughly 200 tons of pure metal, enough to build the shell of a brand new locomotive. The circle closes. A machine that hauled freight for half a century becomes the rail another machine will roll on. A wheel that traveled 1,000,000 kilometers becomes the wheel for the next million. A beam that bore thousands of tons becomes the beam of a new bridge. That's the secret of industrial recycling. Nothing vanishes. Steel outlives any locomotive, any factory, any engineer who forged it. It simply changes shape and starts a new life. Every year, tens of thousands of rail cars and thousands of locomotives reach the scrapyard. Each transforms into new rails, new bridges, new trains, carrying the next generation of cargo across continents. The endless cycle of steel in industrial civilization. Subscribe. We show you how real industrial scale actually works.
Every year, the world produces over 500 billion glass bottles. If you line them up in a single row, they'd wrap around the Earth more than 3,000 times. These are mountains of gleaming, fragile material that could remain in landfills forever, forming glass deserts for thousands of years. But a portion of this material gets a second, third, 100th chance at life. How exactly does an ordinary lemonade bottle, tossed into a recycling bin, pass through fire and mechanical hell to become crystal clear and ready for use again? Behind this lies a colossal technological process that rivals space programs in precision and scale. If you watch to the end, you'll discover the main secret of why glass is called the immortal material, capable of infinite reincarnation without losing quality. And it's precisely this property that makes it a genuine marvel of engineering and ecology. The journey to glass rebirth doesn't start at a factory. It starts on our city streets. Recycling begins with collection. In advanced countries like Germany or Switzerland, this is a well-oiled system where every citizen plays a part. Special containers for clear, green, and brown glass stand on every corner. Moreover, in many European countries, there's a fund system, a deposit included in the beverage price. By returning an empty bottle to a special machine at the supermarket, you receive a voucher that can be used towards purchases. This transforms rubbish collection from a duty into a profitable venture. In other regions, there's an entire shadow army of collectors, people for whom returned bottles are their main source of income. The collected glass flows along logistical arteries, from small trolleys to massive refuse lorries towards recycling plants. It's here, on these noisy and dusty sites, that the first act of its resurrection begins. After tons of glass bottles arrive at the plant, they face their first test, sorting. And this is where technology worthy of science fiction enters the game. Along a wide conveyor belt rushes a motley stream. Clear bottles from water, green ones from wine, brown ones from beer. The human eye can't keep pace with this speed. So optical scanners based on near-infrared technology are installed above the conveyor. A light beam penetrates through the glass while sensors analyze how it refracts. Artificial intelligence determines the chemical composition and color of each fragment in fractions of a second. Color sorting is critically important. Just one green bottle can contaminate an entire ton of raw material for clear glass, giving it an unwanted tint. After identification, the system issues a command. Powerful jets of compressed air shoot with surgical precision at the right fragments, knocking them off the conveyor into separate compartments. But color is only half the battle. Along with glass, the stream contains numerous foreign objects: metal caps, plastic rings, paper labels. Here begins multi-level cleaning. First, the conveyor passes under giant electromagnets. With a deafening clang, they snatch all steel caps from the stream. Then, eddy current separators come into play. They create a magnetic field that repels non-ferrous metals, like aluminum, forcing them to literally jump off the belt into a separate container. After this, powerful fans blow away light rubbish, paper and plastic. And finally, the glass passes through a water cleaning system where organic residue and dirt are washed away. Just imagine the complex journey every bottle we discard takes before becoming clean raw material. After sorting and cleaning, the glass is sent to its execution, the crusher. This is an enormous machine whose steel jaws or hammers grind entire bottles into small fragments with a deafening roar. The sound is as if thousands of chandeliers are simultaneously shattering. Several types of crushers exist: jaw crushers that crush glass between two plates, and hammer crushers where hammers spinning at furious speeds smash glass against a steel wall. This stage's goal is to transform bulky and fragile bottles into a uniform mass called coolant. This material is far more convenient for transport and, most importantly, for melting. At this stage, any remaining impurities not removed earlier can be additionally screened out. After crushing, the coolant is sieved through a system of vibrating screens that calibrate it by size. Even after crushing, coolant may contain microscopic metal or organic particles invisible to the eye, so it undergoes final, even more thorough cleaning. Magnetic separation here works at a new level, capturing the tiniest metal inclusions. Then special optical technologies are used to remove ceramic or porcelain remnants, which look like glass but have different melting temperatures and can cause defects in the finished product. This guarantees that absolutely clean material enters the furnace. Then the glass crumb is sent to vibrating sieves, where it passes through several levels of screens with different mesh sizes for separation into fractions. Different grain sizes are used for different types of products. This entire process is fully automated, minimizing risks for workers. After all stages of cleaning and calibration, the purest cullet is sent to the factory's heart, the melting furnace. At the plant, it's loaded into gigantic furnaces where it melts at temperatures from 1530 to 1650 degrees Celsius. At such heat, glass becomes liquid, viscous, and fiery red, like lava. Adding cullet to the melting process is not just ecological genius, but economic genius too. Recycled glass melts at a lower temperature than primary raw materials, sand, soda ash, limestone, which reduces energy consumption by 30%. Sometimes a small amount of new raw material is added to the melt to adjust the chemical composition and guarantee the strength and transparency of future products. After the glass transforms into a uniform liquid mass, its rebirth begins. The molten lava is directed into forming machines. Here, a drop of molten glass under air pressure transforms into a new bottle, jar, or vase in seconds. At large plants, this process is fully automated and can include high-precision molds to ensure perfect quality. Immediately after forming, the red-hot glass products pass through a long annealing tunnel, where their temperature gradually and very slowly decreases. This is a critically important stage that relieves internal stresses in the glass and prevents cracking. After forming and cooling, new glass products undergo ruthless quality control. Special robotic systems check every bottle for the slightest defects, air bubbles, micro cracks, uneven wall thickness, or incorrect shape. Optical scanners and lasers illuminate the glass, revealing flaws invisible to the eye. If a product doesn't meet the highest standards, it's ruthlessly rejected and sent back for remelting. Then, bottles are tested for mechanical strength, checking whether they can withstand the pressure of carbonated drinks and impacts during transport. Only after passing all these tests are new glass products packaged and dispatched to market. Thus completes one cycle of their endless life.
But an 80,000-ton press isn't just about aviation and space, it's about energy. Massive shafts for hydroturbines, rotors for nuclear reactors, high-pressure housings, all of this demands single-piece forgings of monstrous proportions. Picture a hydroturbine shaft 50 feet long and over 6 feet in diameter. Its weight, more than 100 tons. You can only forge a component like that on a super powerful press. The blank gets heated in a furnace the size of a house, then a crane transfers it onto the press platen, and in just a few strikes, it's shaped into form. Each strike, 80,000 tons of force molding the metal, densifying its structure, squeezing out internal defects. After forging, the part cools slowly, then undergoes heat treatment and machining. But the foundation of its strength, that's laid right there on the press. $80,000 tons. Picture a force that could crush 10 tanks at once. A machine tall as a 10-story building that transforms a red-hot steel mass weighing hundreds of tons into a flat panel like it's Play-Doh. This isn't science fiction. It's the world's most powerful forging press, operating in China since 2013. 80,000 tons of pressure. That's more than the weight of 50,000 cars crashing down on a piece of metal the size of a table. Why did humanity need such monstrous machines? What secrets hide in their history from the Cold War? How did the USSR create a 75,000-ton monster and the US answer with a 50,000-ton press? You'll discover how these metallurgical giants were born, how this inhuman force works, and what can be done under such pressure. Watch till the end. The finale reveals the scale of what humanity creates. The story of giant forging presses didn't start with peaceful purposes. It started with the Cold War arms race. In the late 40s and early 50s, aviation and rocketry demanded fundamentally new solutions. Aircraft were getting bigger, faster, flying higher. Rockets grew in size. And all of this required enormous single-piece components made from high-strength alloys: titanium wing spars, aluminum fuselage panels, steel rocket engine parts. Welding these components together from multiple pieces weakened the structure. Welded seams were vulnerable under load and vibration. What was needed was a technology capable of forging a giant part as a single piece, no seams. That's how the idea of ultra-powerful hydraulic presses was born. The United States understood this first and built several presses in the 50s, capable of exerting up to 50,000 tons of force. The Soviet Union wasn't about to be left behind. At the height of the space race and the arms race, the USSR built a 75,000-ton forging press, an absolute record at the time. The giant machine stood in the factory floor like a metal cathedral, dozens of meters tall, hundreds of tons of structure, hydraulic cylinders as thick as a human body. This press allowed the Soviet Union to stamp out parts for rockets, submarines, and aircraft on a scale that was previously impossible. A solid titanium component several meters long, no longer a dream, but reality. 75,000 tons of force meant that metal of any hardness became pliable material. The Cold War fueled technological progress, and these forging giants were one of its symbols. For decades, these presses remained the pinnacle of engineering. But in 2013, China shattered all records. At one of their metallurgical plants, they fired up a hydraulic press with a force of 80,000 tons. 80,000 tons? That's a force that's hard to wrap your head around. It's the weight of a major ocean liner crashing down on an area the size of a dining table, or pressure equivalent to 50,000 cars stacked on top of each other. The scale of this press is mind-blowing, as tall as a 10-story apartment building, weighing thousands of tons of steel and cast iron, with massive hydraulic systems capable of generating this monstrous force. This press didn't just break a record, it opened up a whole new era of possibilities. Now you can stamp out parts of sizes that used to be considered impossible. Panels for jumbo jets, components for space rockets, reactor equipment, all of this became achievable thanks to this machine. How does a giant like this work? The foundation is hydraulics. Picture massive cylinders filled with oil under monstrous pressure. When pressurized oil flows into the cylinder, the piston starts to move. But this isn't your ordinary piston. Its diameter measures in yards, and its stroke spans dozens of yards. Slowly, but with unimaginable force, the piston descends to where a glowing metal workpiece sits on a massive plate. The workpiece weighs hundreds of tons, a huge ingot of steel, titanium, or aluminum, heated to around 2200 degrees. The metal glows bright orange, radiating unbearable heat. The shop floor fills with the roar of hydraulics, the smell of hot metal and oil. And then the upper plate of the press begins its descent. Slowly, almost ceremonially. But behind that calm lies 80,000 tons of force. Contact. The upper plate of the press touches the red-hot blank, and the miracle of deformation begins. Metal that's hard as rock at room temperature starts flowing like thick paste under this kind of pressure. 80,000 tons don't give the metal a choice. The blank flattens, spreads outward, takes the shape of the die. A thick ingot becomes a flat panel or a complex three-dimensional part. The process is accompanied by deafening thunder. The metal cracks, groans. Excess material squeezes out, flowing to the sides in glowing streams. Temperature, pressure, force, all controlled by computers with millimeter precision. The slightest mistake and a multi-ton blank is ruined, or worse, the press itself can fail. But the operators know their craft. One stamping cycle takes minutes, but the result is a seamless part with perfect internal structure. Why does this matter so much? Because a single forged part is stronger than any welded structure. A weld seam is always a weak point. Under load, vibration, cyclic stress, that's where cracks start. In aviation or spaceflight, a crack means catastrophe. That's why major structural elements, aircraft wing spars, fuselage panels, landing gear components, rocket engine parts, must be one piece. A super heavy press can forge a titanium beam 30 feet long with no joints whatsoever, or an aluminum panel the size of half a Boeing wing, or a steel blank for reactor equipment weighing 400,000 pounds. Parts like these used to be welded together from dozens of pieces. Now they're made in one press stroke. It's a revolution in manufacturing.
China didn't build this press by accident. The country is aggressively developing its aviation industry, space program, and nuclear power. All of this demands technologies that were previously only available to the US and Russia. An 80,000-ton press is a declaration of technological leadership. Now China can manufacture components it used to have to buy from abroad or settle for smaller dimensions. This is strategic independence. When you've got a press like this, you can build your own aircraft, your own rockets, your own reactors without relying on someone else's technology. It's no coincidence that information about the exact specs and capabilities of this press is tightly controlled. This isn't just manufacturing equipment, it's an element of national security and technological sovereignty. There are only a handful of these presses in the world. Russia has kept its Soviet-era 75,000-ton giants still running in defense plants today. The US operates its 50,000-ton machines, built back in the 50s and 60s. China now leads with 80,000 tons. There are projects for even more powerful presses, 100,000 tons and beyond. But each of these machines represents a colossal investment. Building a super heavy press costs hundreds of millions of dollars. You need a special foundation that goes dozens of feet into the ground. You need massive hydraulic systems, furnaces to heat the billets, cranes with lifting capacities in the hundreds of tons. It's an entire complex covering the area of a football field. But the payoff is worth it, the ability to manufacture parts that nobody else can. And just like that, through the Cold War, through the technology race between superpowers, through decades of engineering development, humanity arrived at the 80,000-ton press. This isn't just a machine, it's a symbol that we've learned to dominate matter with a force comparable to geological processes. When 80,000 tons come crashing down on white-hot metal, it's like watching the Earth's crust crumple into mountains under tectonic plates. Except here, this process is controlled by humans. Every part that comes out of a press like this carries the imprint of unimaginable force and precision. Planes fly, rockets shoot into space, reactors generate power, and behind all of it stand these giant presses, crushing metal like Play-Doh. This is the story of how humanity learned to create the force of gods and use it to conquer the sky, space, and the atom.
Hey everyone, on this channel we go behind the scenes where cameras usually aren't allowed. If you're into this kind of breakdown, hit subscribe and tap that bell so you don't miss new episodes. Every year, the world recycles over 1.5 billion tons of scrap metal, and hidden within this chaos of rust and mangled iron is something way more valuable than it looks. What seems like trash today could save your life tomorrow at 75 miles per hour. But how exactly does this pile of metal transform into a precision-engineered component trusted by millions of drivers? And why can even a tiny 1% error destroy an entire batch? There's one detail in this process almost nobody talks about, and it's what determines whether your car stops when it really matters. Today, we're breaking down the entire production of brake rotors, from the furnace to final inspection. It all starts with what most people would just call a junkyard. And that's pretty ironic. What will later stop your car at 75 miles per hour, right now looks like a giant pile of rusty junk. Old cast iron radiators, car body fragments, twisted beams, and other metal scrap. It's all stacked in heaps on the lot outside the plant, and rain sends rusty orange streaks running down into the asphalt. But to this factory, it's all treasure. A massive electromagnet hanging from a crane scoops up several tons of this iron and drops it with a crash into the throat of a giant induction furnace. Induction, meaning the metal doesn't melt from fire, but from an electromagnetic field that heats it from the inside out, evenly and fast. If you stand too close, it's kind of terrifying. The furnace hums at such a low frequency that you don't really hear the sound. You feel it deep in your chest, like your heart's trying to sync up with this heavy industrial rhythm. The temperature inside the furnace climbs to 2,700 degrees Fahrenheit. At that kind of heat, even the toughest steel turns into liquid, more like glowing, ridiculously dangerous soup than anything solid or dependable. When the furnace tilts to pour out the molten metal, everything around you floods with bright orange light that makes you want to squint. No artificial beauty here, just brutal physics and an insane amount of heat. Every batch of metal gets tested instantly. Lab techs in special suits grab a small sample, cool it down, and within seconds determine its chemical makeup using a spectrometer. The device breaks the sample down into elements and spits out precise percentages of each component. If the carbon or silicon content deviates from spec by even 1%, the entire massive batch gets sent back for remelting without hesitation. Mistakes aren't tolerated here, because the cost of that kind of error to the end user could be way too high. Next, they pour this liquid fire into molds. They use sand casting technology here. Sand seems like an unreliable material, but at this factory, they mix it with special resins and under enormous pressure, it becomes hard as concrete. The molds are made with jeweler-like precision. The internal relief copies every detail of the future disc, including cooling fins and mounting holes. Metal fills the cavities inside the sand mold, and it's at this exact moment that the rough blank of the future brake disc is born. It doesn't look anything like that shiny part we're used to seeing in auto parts stores yet. Instead, it's something big, heavy, and really dirty. After pouring, the discs need to cool naturally. It's a long process, sometimes taking several hours, and this is critically important. If you try to speed up the cooling, say by splashing water on it, the metal becomes too brittle. A disc like that could just shatter into pieces at the first hard stomp on the brake pedal somewhere out on the highway in the rain. When the blanks cool down to just warm instead of glowing red hot, they head to the machining shop. This is where robot territory begins. They work 24/7, no lunch breaks, no complaints about tough working conditions. Each disc gets grabbed by a manipulator arm that loads it into a CNC machine. Special cutting tools shave off excess metal as easily as if it weren't solid cast iron, but a stick of cold butter. Chips spiral out red hot and drop into a collection tray while a smooth, precisely calibrated surface emerges from under the cutter. At this stage, fanatical precision rules. A deviation of 0.8 of a millimeter means hopeless scrap. A disc like that never makes it to the warehouse because it'll cause vibration that'll just destroy a car's suspension in a few months and force the driver to shell out a ton of cash for repairs. The machine finishes one disc in several minutes, and each one comes out identical to the last. Robots don't get tired and don't lose focus by end of shift. It's fascinating to watch as the perfect, almost mirror-like surface gradually emerges from a rough and ugly form. Then they drill ventilation holes and internal channels into the discs. This isn't done for visual style like some people think. It's a critically necessary cooling system, without which the discs simply wouldn't survive serious loads. During heavy braking, the disc can heat up to 1,300 degrees Fahrenheit. At that temperature, it glows dark cherry red. If this heat isn't removed in time, the metal starts losing its friction properties, and the brakes just disappear at exactly the wrong moment. So these holes and channels, they're the result of extensive engineering calculations, not some design decision for looks. Each channel has a precisely determined diameter and angle, calculated so airflow pulls heat away from the working surface as efficiently as possible. Once all the excess shavings are removed, each rotor gets sent to dynamic balancing. It's a lot like what they do to your wheels at the tire shop, but the precision here is tens of times higher. A special device spins the rotor up to enormous speed and uses sensors to detect the slightest weight imbalance. At these rotational speeds, any imbalance turns into noticeable vibration, and the machine picks it up with gram-level accuracy. If one side turns out to be heavier by even 3 or 4 grams, the machine automatically drills out a tiny, nearly invisible dimple in just the right spot on the face to even out the weight. After that, the rotor is perfectly balanced and ready to perform at any RPM without any extra noise or judder. It's at this stage that the difference is made, whether the driver will feel every imperfection through the pedal or whether braking will stay smooth and silent at any speed. I asked the chief engineer how many of these rotors they produce in a single full workday. He just smiled wearily and said they stopped counting them individually a long time ago. They track output in thousands of tons of finished product per month. Just think about that for a second. This facility supplies parts for nearly half the European automotive market, which means every other car you see on city streets is probably stopping with rotors made right here, in this loud, scorching hot plant. Before packaging, the rotors go through a protective coating process. They're either painted with a special heat-resistant paint or coated with a thin, anti-corrosion, zinc-based layer. The coating gets applied in a chamber, the rotor hangs from a conveyor, and automatic sprayers evenly cover it from all sides. This is done so they don't turn into a rusty chunk of metal during long-term warehouse storage or while crossing the ocean in a shipping container. Sure, after the first few miles of driving, this paint on the working surface will completely wear off under the massive friction from the brake pads, but the edges and internal parts will stay protected from road salt and grime. The final, and arguably most critical stage, is the quality control check. And we're not talking about some tired worker giving it a quick once-over at the end of their shift. They use ultrasonic scanners and X-ray machines. They're hunting for internal defects, air bubbles or micro cracks you couldn't spot even with a magnifying glass. Ultrasound sends a wave through the metal, and if there's a void inside, the signal bounces back distorted. The machine flags the problem zone instantly. Even if the disc looks flawless on the outside, but the X-ray reveals a cavity just 2 millimeters wide somewhere deep in the metal, it gets sent straight to the shredder. Nobody cuts corners on safety here, because everyone knows full well, this part directly determines whether the driver and passengers live or die. A plane that looks like a whale flies through European skies. It doesn't carry passengers, it carries other planes. Wings 100 feet long, fuselage sections as tall as a house. This is the Airbus Beluga XL, Europe's biggest cargo plane, 112 tons of freight, a cargo hold 29 feet across. Inside, it can fit 2 Airbus A350 wings at once. Without the Beluga, Airbus production would stop in a week. Today, we'll see how this giant is born, from an aluminum sheet to the first roar of its turbines. The Beluga XL is a puzzle made from parts created at 5 points across Europe. The base, an Airbus A330. Its lower fuselage, wings, and landing gear are assembled in Toulouse. But the nose section? That's made by Stelia at their plant in Mayotte, France. 40 feet long, 18 tons. Inside, the cockpit, avionics, hydraulics. All on a plug-and-fly principle. Panels from aluminum alloy 2024 with copper and magnesium are formed on presses capable of 1,300 tons of force. The frame is assembled from bulkheads and stringers, then the skin is riveted on top. 12,000 rivets, each about 1/6 of an inch in diameter for a single nose. The upper expanded fuselage, the heart of the Beluga, is produced by Premium Aerotech and Dehard. 3 sections, 2 side panels and a roof. 29 feet in diameter, nearly 6 feet wider than the previous Beluga. Sheet thickness ranges from 1/10 to 1/4 inch. Each panel is reinforced with 30 stringers. Bulkheads are placed every 20 inches. Everything's riveted and bolted with titanium bolts, torqued to 90 foot-pounds. The cargo door, an engineering marvel. Stelia Rochefort, France. 33 feet long, 26 feet high. Area nearly 1,500 square feet, like a basketball court standing vertical. Weight 3.1 tons. Frame made from titanium alloy, Ti6Al4V. Titanium handles the loads. 24 latches hold the door, 12 on each side. Each latch clamps down with 3 tons of force. The door opens with 4 hydraulic cylinders, Piston diameter 4.7 inches. Pressure 4,000 psi. 3 minutes to open, 4 to close. Inside the door, hundreds of yards of wiring and hydraulic lines. They shipped the door from Rochefort to Toulouse on a barge, the same one that carried A380 sections. By sea to Bordeaux, by river to Langon, then 125 miles by road. The tail section, modified by Spain's Aeronova in the Basque Country. The vertical stabilizer increases by 50%, from 33 to 50 square feet. The massive bloated fuselage creates serious drag. You need stability. They add vertical end plates to the horizontal stabilizer, plus 2 ventral fins under the tail. 5 vertical surfaces total instead of 1. Everything's made from composites, carbon fiber. Layers of carbon fabric soaked in epoxy resin, laid in a mold and into the autoclave. 360 degrees Fahrenheit, 100 pounds per square inch, 8 hours. The composite fin weighs 1,300 pounds instead of 2,000 aluminum. December 2016, Toulouse. Line L34, a hangar spanning 130,000 square feet. Final assembly of the first Beluga. Lower fuselage with wings from an A330 goes on the jig. From above, a 50-ton crane lowers the expanded upper fuselage. They mate the perimeter. Hundreds of bolted connections. They drill quarter-inch holes through both sections at once, tolerance plus or minus 0.04 of an inch. Bolts get torqued with computer-controlled wrenches. The joint sealed with polysulfide compound, works from -76 to +250 Fahrenheit. They mount the nose section, tail, vertical stabilizer. 3 months of work. Meanwhile, the guts. 50 miles of wiring in bundles of 50 to 100. 2,000 feet of stainless hydraulic lines. Pressure 4,000 pounds per square inch. 12 fuel tanks. 37,000 gallons of kerosene. March 2018. Engine installation. 2 Rolls-Royce Trent 700s. Each one weighs 12.3 tons. Thrust? 320 kilonewtons, 72,000 pounds of force. Fan diameter? 9 feet. 24 composite blades with titanium leading edges. The engine mounts to the wing through a titanium pylon with 4 bolts, each 1.9 inches in diameter. Torque? 2,950 pound-feet. 37 connections to each engine. Fuel, electrical, hydraulic, pneumatic. April through June, ground testing. 200,000 checkpoint inspections. Every sensor checked, every actuator verified. Flight control checks. Elevators deflect 25 degrees up, 15 down. Ailerons, 25 up, 15 down. Laser sensors monitoring. Accuracy to within 0.5 degrees. July 19, 2018. Blagnac, Toulouse. First flight, crew of 6, 150 sensors recording 200 parameters 1,000 times per second. Takeoff thrust 96%. Turbine exit temperature 2,700 degrees. Fuel burn 12 tons per hour. 120 knots, 222 kilometers per hour. Nose wheel liftoff. 140 knots, main gear liftoff. Climb rate 1,000 feet per minute. Flight level 350, 35,000 feet. Cruise speed 0.69 Mach, 466 miles per hour. 4 hours, 20 minutes airborne. Landing nominal. Next up, flight test program. 200 flights, 700 hours. Maximum weight with ballast, 51 tons. Single engine flight. Crosswind landing at 30 knots. minus 22 in Sweden, plus 113 in Spain. Everything works. November 13th, 2019. Type certificate. The Beluga cleared for flight. January 9th, 2020. First commercial flight. Toulouse, Bremen, Toulouse. Cargo, 2 A350 wings, each 105 feet long, 21,000 pounds. Before, 2 flights with the old Beluga. Now, 1. Loading 70 minutes. Wings roll in on a trolley along floor tracks. 24 tie-down points with straps. Flight 1 hour 40 minutes. In Bremen, they unload the wings, load A320 fuselage sections, fly to Toulouse. 3 to 4 flights a day, 6 days a week. 1,000 flights a year across 6 aircraft. Without the Beluga, Airbus wouldn't build a single plane. Wings made in Great Britain, tails in Spain, fuselages in Germany, final assembly in Toulouse and Hamburg. The Beluga, a flying assembly line. Europe's industrial artery. 1 billion euros program cost, 167 million per aircraft, 30 years of service, 60,000 flight hours. If this was interesting, hit like. Did you know about the Beluga? Write in the comments. Subscribe. Here we show you factories you never knew existed. Hey folks, on this channel, we go where cameras usually aren't allowed. If you dig these behind-the-scenes deep dives, hit subscribe and smash that bell so you don't miss new episodes. Today, I'm showing you how they make those manhole covers we walk over every day without even thinking about it. Turns out, it's way more interesting than you'd expect. I'm standing in the middle of a foundry floor, and it's about 110 degrees Fahrenheit in here. Sweat's pouring down like crazy, my glasses are fogged up, and the air's thick with the smell of molten metal and coal. Black coke dust crunches under my feet, and in the distance, a furnace pulses with a crimson glow. Come with me. I'll show you everything from the first ladle of molten metal to the finished cover. I'm met by the foundry master, a man in his 60s, with hands scarred by thousands of sparks. He's worked here for 38 years and says he's seen manhole covers cast for every major city. His creations lie everywhere beneath our feet. It all starts with scrap metal, massive piles of old cast iron, engine fragments, pipes, radiators, even old manhole covers that have served their time. Cast iron can be remelted an infinite number of times without losing its properties. It's one of the few things humanity gets right. Metal recycling here is 100%. The scrap is sorted by composition, weighed, and crane-loaded into a cupola furnace, a massive furnace about 30 feet tall, resembling a medieval tower. Inside, layers of coke and cast iron scrap alternate. The coke burns at around 2,700 degrees Fahrenheit, and at that temperature, the cast iron melts, transforming into a glowing orange liquid that flows to the bottom of the furnace. I stepped closer, as close as safety regulations would allow, and felt the skin on my face instantly tighten from the heat. At 15 feet, the temperature is so intense you want to back away. But the workers stand right by the furnace in special reflective suits, looking like astronauts. When the iron's melted, they release it into a ladle, a massive metal scoop that holds about 2,000 pounds. The ladle hangs from a crane and glides smoothly over rows of sand molds laid out across the factory floor. Each mold is the negative of a future manhole cover, an imprint of every detail, every letter, every ridge. The molds are made from special sand mixed with clay and water. A master craftsman showed me how it works. They take a wooden or metal model of the cover, press it into the sand, then carefully lift it out. What's left is a perfect impression. Every line, every curve, copied with accuracy down to a few thousandths of an inch. They place the second half of the mold on top, and you've got a cavity ready for the metal. A single model can produce thousands of impressions before it needs replacing. The coolest part? The text on the manhole covers. Each one shows the name of the city or water department. The letters are made separately. Small wooden or plastic type pieces get pressed into the sand in just the right spots. When the iron hardens, the text pops out. That's why all the words on manhole covers are mirror images of what was in the mold. Now comes the most spectacular part, the pour. Two workers in silver suits tilt the ladle, and out flows a stream of molten iron. It glows so bright you can't look at it without protective glasses. Your eyes start watering after a couple seconds. The metal hits 2,600 degrees Fahrenheit. The iron fills the mold in 5 seconds flat. But you've got to pour carefully. Too fast and the metal traps air, creating pockets inside the manhole. That cover will be weak and could crack under the weight of a truck. Too slow and the metal starts hardening on the way down, filling the mold unevenly. An experienced foundry worker feels the right speed instinctively. It's a skill that takes years to develop. The sand mold starts smoking after the pour, moisture from the sand and clay evaporating. The smoke is thick, gray, smells like scorched earth. Ventilation runs full blast, but visibility in the shop still drops to about 50 feet. Then comes the waiting. The iron needs to cool, but not too fast. Slow cooling is what gives the metal its proper structure and strength. Open the mold too early, and the manhole cover warps from the sudden temperature shift. Scrap. The sweet spot is 18 hours. During that time, temperature gradually drops from about 2,550 degrees Fahrenheit down to around 210. The molds sit in rows on the shop floor, radiating steady, dry heat, like a radiator. Next day, workers smash the sand molds with hammers, and out come the manholes, still hot, dark gray, coated in sand residue. They look rough, messy, nothing like those smooth covers lying in the streets. Each manhole cover weighs between 66 and 132 pounds, depending on the size. A standard cover for city sewers runs about 24 inches in diameter and weighs roughly 95 pounds. I tried lifting one, barely got it off the ground. The foreman laughed. He's been lifting 10 of these a day for nearly 40 years. Next, the covers go to processing. A special machine with rotating steel cable brushes cleans off any remaining sand. Sparks fly in every direction. The metal gradually takes on a clean gray color. Pneumatic hammers knock off the flash, leftover metal that solidified in the wrong places. The most critical step is machining the seating surface. The cover's edge has to fit the frame perfectly or it'll rattle under traffic. Tolerance, about 1/10 of an inch. A lathe turns the edge to perfect roundness, and every cover has small holes, 2 or 4. They're for the special hook utility workers use to pull covers out. Without them, lifting a 95-pound cast iron lid off a flat surface is basically impossible. The quality control here is amazing. An inspector just taps each manhole cover with a small hammer and listens to the sound. If the sound is clean and ringing, the cover's good. If it's dull or has an off tone, there's a crack or void inside somewhere, and that cover gets scrapped. He checks 200 covers a day and says he's never wrong. I ask why manhole covers are round. Seems like square ones would be simpler to make. The foreman explained something brilliantly simple. A round cover can never fall through its own hole. A square one can be turned diagonally and drop right down. A circle is always bigger than its opening, no matter how you turn it. That's why manhole covers are round all over the world. It's not tradition, it's math. Another detail, the pattern on the surface. Those grooved lines, stars, or grid patterns aren't there for looks. It's an anti-slip coating. Smooth cast iron in the rain is slippery as ice. With the ridges, traction is way better. I stood on one cover right there in the shop, held firm even in work boots with smooth soles. Finished manhole covers get stacked 10 to a pile and shipped out to cities. Each stack weighs around 900 to 1,100 pounds, so they only load them with a crane. One factory produces 50,000 covers a year. Sounds like a lot, but a major city alone might have over 300,000 manholes. That means every few years, every single cover needs replacing. Why so often? The covers break down. Sand and salt in winter, vibrations from trucks, temperature swings from -22 to 130 Fahrenheit on the asphalt in summer. Cast iron is tough, but it's not forever. Average lifespan is 30 years, and in high-traffic areas, just 5. There are covers for steam tunnels, telephone, electrical, water mains. Each type differs slightly in size and thickness. The thickest ones are for highways, where they get run over by trucks weighing 36 tons. There, the wall thickness hits 2 inches. The Factory Museum holds old manhole covers, the oldest one from 1892. Over 130 years old, and it's still intact. The cast iron's dark, smooth from time, but not a single crack. There are covers from different countries: France, Japan, England. The Japanese ones are the most beautiful, engraved with cherry blossoms or mountains. Over there, manhole covers are art. When I left the factory, there was an ordinary manhole cover lying in the street. I stopped, crouched down, ran my hand across its surface. Now, I see it differently. This isn't just a lid. This is 2,700 degrees of heat, 18 hours of waiting, precision down to 1/10 of an inch, workers' hands in silver suits, and the ring of an inspector's hammer. Every manhole cover beneath our feet has been through this journey and will last another 30 years, bearing thousands of tons, millions of footsteps, rain, snow, and heat. Picture a metal that's everywhere in nature, yet remains one of the most expensive and difficult materials for industry to work with. That metal is titanium. It's abundant in the Earth's crust, but producing it is so labor-intensive, energy-hungry, and technologically finicky that the aviation industry literally fights for every quality pound. And that's not an exaggeration. Without titanium, there'd be no modern jet engines, no critical aircraft components, no landing gear parts, no structural elements where you need high strength, low weight, and corrosion resistance all at once. But the journey of titanium from black sand or ore concentrate to an aircraft part is remarkably far from conventional metallurgy. You can't just melt it down, reduce it with carbon, and pour it into a mold like steel or iron. Titanium is too reactive. It bonds with oxygen way too easily. It's too sensitive to contamination. And that's exactly why producing titanium for aviation isn't just mining and smelting. It's one of the most complex sequences of chemical and metallurgical operations in modern industry. In nature, titanium almost never occurs as pure metal. Industry extracts it from minerals, mainly rutile and ilmenite. Very often, these ores aren't mined in classic deep mines, but in what are called mineral sands, placer deposits that form along coastlines and in ancient sedimentary zones. This means the first stage of titanium production looks totally different from the typical picture of miners and mine shafts. Here, they might use dredges, excavators, washing systems, gravity and spiral separators that separate heavy minerals from lighter waste rock. But even after processing, what you have isn't metal yet. It's just titanium-bearing raw material. And this is where the main paradox kicks in. Titanium is extremely abundant, but extracting actual metallic titanium from its oxides is way harder than smelting many far rarer metals. That's exactly why titanium is expensive, not because it's rare in nature, but because turning ore into aviation-grade metal is brutally complex. The next stage is converting the ore into a chemical form from which pure metal can actually be extracted. For titanium, this is especially critical because the usual heat-based reduction doesn't work here. While iron or copper can be processed using relatively straightforward metallurgical methods, titanium is a different beast. Its oxide is too stable, and the metal itself, at high temperatures, binds too aggressively with oxygen, nitrogen, and carbon. So industry takes an indirect route. Titanium feedstock is first converted into titanium tetrachloride, a volatile chemical compound that can then be purified. To do this, the concentrate undergoes high-temperature chlorination in the presence of a reducing agent, and then the resulting product is sent for purification. The key advantage of this approach is that titanium tetrachloride can be purified through distillation, removing a whole range of unwanted impurities. Essentially, this is the moment when rough mineralogy transforms into chemically controlled feedstock for the metal to come. And it's at this stage that it becomes clear. Titanium production isn't classic smelting. It's a chemical metallurgical process with extremely tight purity requirement. Once the purified titanium tetrachloride is ready, one of the industry's most critical processes kicks in, the Kroll process. This is the fundamental industrial technology that makes modern mass production of titanium for aviation, aerospace, and other high-tech fields even possible. Here's how it works. Purified titanium tetrachloride reacts with molten magnesium inside a sealed reactor. The result? The metal breaks free from chlorine and forms what's called titanium sponge. This isn't a solid ingot or finished semi-product yet. It's a porous, brittle metallic mass that looks like hardened porous rock. After the reaction, leftover magnesium and byproducts get removed. Then the sponge is sorted, crushed, and prepped for the next stage. At first glance, you might think the sponge is almost finished metal, but really, it's only halfway through a long journey. Aviation doesn't just need titanium, it needs material with precise chemical composition, high uniformity, and predictable behavior under stress. So next, this sponge still has to be transformed into a full-fledged structural metal. The next major stage is remelting the titanium sponge into a dense, homogeneous ingot. And this is where production gets especially tricky again. Molten titanium aggressively absorbs oxygen, nitrogen, and other impurities from the surrounding environment. Even slight contamination can make the metal brittle and unsuitable for critical aircraft components. That's exactly why titanium remelting doesn't happen in a regular shop floor atmosphere. It's done in a vacuum or a controlled inert environment. One of the key methods is vacuum arc remelting. For this process, they form a consumable electrode from titanium sponge, alloying additives, and sometimes a portion of quality scrap returns. Then, this electrode is gradually melted by an electric arc, and the metal collects drop by drop in a water-cooled mold, forming an ingot. For critically important aerospace applications, a single remelt like this often isn't enough, so the metal may go through double or even triple remelting to achieve maximum structural uniformity, stable composition, and the absolute minimum number of defects. But aviation doesn't just need pure titanium. In most cases, the foundation is special titanium alloys, and the most famous of these is Ti6Al4V, also known as Grade 5. In this material, titanium is alloyed with aluminum and vanadium to achieve a combination of properties that's practically impossible to replicate in many other metals. This alloy is noticeably lighter than steel, yet it has very high specific strength, good fatigue resistance, and outstanding corrosion resistance. That's exactly why it's used in compressor discs and blades of aircraft engines, in landing gear components, structural load-bearing elements of the aircraft, and other assemblies where every pound matters. But for titanium to become a true aerospace material, it's not enough to just melt it into an ingot. What follows is forging, rolling, heat treatment, microstructure control, and mechanical property verification. In other words, aerospace-grade titanium isn't just a metal, it's an entire series of carefully sequenced operations, each one affecting the final reliability of a part that will later operate under enormous loads. This is where it becomes clear why titanium is so expensive. First, production isn't continuous, it's largely cyclical. The Kroll process is slow and energy-intensive. It requires magnesium, chlorine, sealed reactors, and complex purification afterward. Second, almost every hot stage demands a vacuum or inert atmosphere. Why? Because the metal reacts too aggressively with oxygen. Third, titanium itself is a nightmare to machine. It has low thermal conductivity. Heat doesn't escape into the chips. Instead, it concentrates on the cutting tool. This accelerates tool wear, slows down machining speeds, and drives up the cost of every finished part. On top of that, titanium semi-finished products require extremely precise control of structure and chemistry, and tolerances in aviation are far tighter than in mass industry. The bottom line, titanium isn't expensive because it's rare in nature. It's expensive because the entire chain, from ore to aerospace-grade alloy, is extraordinarily complex, long, and sensitive to any deviation from the process. There's one more reason titanium is so valued specifically in aviation. It fits perfectly into the philosophy of modern engineering, where weight savings directly translate into efficiency gains. A lighter aircraft burns less fuel, carries more payload, and its engine and structural components operate in more favorable conditions. But titanium isn't a universal replacement for steel or aluminum. It's used where it truly justifies its cost, in hot sections, highly stressed components, corrosive environments, and parts where the combination of strength and low weight is critical. That's why titanium production for aviation isn't just metallurgy for the sake of metal. It's an industry where every step serves a single purpose: to create a material that will perform reliably in an aircraft at high speeds, under cyclic loads, vibrations, temperature swings, and with enormous responsibility for safety. When you look at titanium's entire journey, you're witnessing a nearly perfect example of modern high-tech manufacturing. First, heavy mineral sands or ore concentrates get separated from waste rock. Then, chemical processes transform the raw material into purified, volatile compounds. Next, through the Kroll process, they obtain porous titanium sponge. After that, it's remelted into ingots under vacuum, alloyed, structurally and chemically refined several times over, and only then transformed into semi-finished products and parts for aviation. In other words, titanium's journey is a path from dirty natural mineral to a material that can work inside a jet engine or an aircraft structural assembly. And perhaps that's where titanium's real power lies. It seems like just another element in Earth's crust, but actually becomes a true engineering marvel only after incredibly complex technological processing. That's why aviation-grade titanium isn't just a metal. It's the embodiment of how far industry can push when it needs the perfect balance of strength, lightness, durability, and reliability.
There's something almost poetic about watching a massive steel plate, thick as your fist, transform into a perfect cylinder. What we're seeing here is one of Central Europe's finest engineering firms working with a steel plate 4 3/4 inches thick, nearly 10 feet wide, destined to become a cylinder with a 55-inch diameter. For those of us who remember when heavy industry was the backbone of manufacturing, this is the kind of craftsmanship that built the world we know. The star of this operation? The plate rolling machine. And let me tell you, this Italian marvel is about as perfect as metalworking equipment gets. The company's been perfecting this craft since 1946, right after World War II, when Europe needed reliable machinery to shape the infrastructure of the modern age. The machine operates on a 3-roller pyramid principle, which has been the gold standard for rolling heavy plates since the Industrial Revolution, though the precision we're seeing here would have blown the minds of craftsmen from that era. Here's how this beautiful process unfolds. A steel plate, which has been preheated to reduce brittleness, gets positioned between three massive cylindrical rollers arranged in a triangular configuration. The two bottom rollers are the driving force, rotating in synchronized harmony to pull the plate through, while the top roller, which can be hydraulically adjusted to within fractions of a millimeter, applies downward pressure, creating the curvature. Think of it like rolling out dough, except this dough weighs several tons and could support a building. The operator, working from a computerized control panel, inputs the desired diameter and thickness parameters. The machine's sophisticated sensors continuously monitor the bend radius, making real-time adjustments through hundreds of hydraulic cylinders. Remarkably, despite working with such massive forces, the machine achieves tolerances that would make a Swiss watchmaker proud. The plate makes multiple passes through the rollers, bending a little more each time, gradually approaching that perfect cylindrical form. This incremental approach prevents stress fractures and ensures uniform curvature along the entire length. As the plate begins its transformation, you can actually see physics at work. The outer surface of the bend stretches while the inner surface compresses, and the metal flows like frozen honey, maintaining its structural integrity while taking on this new shape. Now, let's step into the world of heavy forging, where tradition stretches back to the blacksmiths of ancient Rome. Except now we're working with hammers that make Thor's hammer look like a toy. What's especially mesmerizing is the combination of raw power and surgical precision. We're watching parts being forged that can weigh up to 250 tons. The process begins long before the hammer ever strikes. Steel ingots, fresh from the mill, are slowly heated in gas furnaces to temperatures around 2,200 degrees Fahrenheit. This isn't a rushed process. Depending on size, heating can take anywhere from 8 to 24 hours. Once the steel reaches that perfect forging temperature, glowing that unmistakable orange-yellow color that means it's ready to flow, the real dance begins. Massive manipulators, essentially industrial robotic arms that can rotate and position these multi-ton pieces with remarkable delicacy, move the workpiece under the forging press. Both hydraulic presses and mechanical hammers are used, depending on what the job demands. A hydraulic press applies slow, steady pressure, ideal for ensuring the force penetrates deep into the heart of the piece, eliminating any internal voids or inconsistencies. The mechanical hammer, on the other hand, delivers rapid blows that shape the surface and create specific forms. The forge master, a craftsman whose skills require decades to develop, orchestrates this symphony of heat and pressure. Between each strike or pressing, the piece rotates, gets repositioned, and sometimes reheated. This is called open die forging, because unlike closed die forging, where metal is compressed into a specific shape, here the masters are literally sculpting the metal through repeated strikes and pressure applications, gradually drawing it into the desired form. Each strike refines the grain structure, making the steel stronger and more reliable than anything achievable through casting or machining alone. Now let's move on to modern precision forging, which has adapted traditional forging techniques to produce complex automotive and industrial components at volumes that would have been unthinkable in the old days of small batch artisan forging. The process starts with steel bars, often supplied in coils, which are cut to precise lengths and then fed into induction heating systems. Induction heating is one of those technologies that seems almost magical when you first encounter it. No flame, no combustion, but within seconds a steel billet placed inside an induction coil glows cherry red, then orange, then that brilliant yellow-white that tells you it's ready for forging. The secret lies in electromagnetic induction, discovered by Michael Faraday way back in 1831, but only practically applied to industrial heating in the early 20th century. Alternating current flowing through the coil creates a rapidly changing magnetic field, which induces electrical currents in the steel itself, and these currents generate heat through resistance. After heating to the optimal forging temperature, typically between 2,000 and 2,300 degrees Fahrenheit, Depending on the steel grade, the billet moves to the forging press. Sophisticated closed die forging is used, where the hot steel is placed between two die halves that contain the negative impression of the desired part. When these dies come together with thousands of tons of force, the steel has nowhere to go but to fill every contour of that cavity. What's remarkable is the speed and precision of modern forging presses. We're talking about machines that can complete a forging cycle in just a few seconds, yet achieve dimensional tolerances that would have required extensive machining in the past. There's something deeply satisfying about watching skilled craftsmen build storage tanks. The process begins with selecting and cutting steel plates. Modern fabrication shops use CNC cutting tables, plasma or laser, that can slice through thick steel plate with remarkable precision, following computerized patterns that ensure minimal waste. But before any cutting happens, there's meticulous layout work, figuring out how to arrange different components to get the most from each plate. It's a puzzle that combines geometry, efficiency, and materials science. After cutting, the components move to rolling and forming operations. Tank shells typically need to be cylindrical, which means flat plates must be rolled into curves using 3-roll bending machines like the ones we saw earlier. The edges of these rolled sections are then prepped for welding, usually with beveled cuts that let the weld penetrate completely through the material's thickness. The welding process, that's where the craftsmanship really shines. Tank fabrication typically uses submerged arc welding for the main seams, a process where the arc works under a blanket of granular flux, protecting the weld from atmospheric contamination while allowing deep penetration and high deposition rates. End caps, whether they're flat, dished, or hemispherical, get fitted and welded on, and then comes the real test, hydrostatic testing. The completed tank gets filled with water and pressurized above its operating pressure to verify integrity. Any leaks or weaknesses show up here, not during service, which could be catastrophic. Let's wrap up with the 3-roll plate bending operation, because there's something fundamentally impressive about watching these machines transform flat steel into curves with such apparent ease. The 3-roll bending machine is one of those elegant engineering solutions that's remained fundamentally unchanged for over a century because, simply put, it works beautifully. The machine consists of 3 essential rollers arranged in a pyramidal or triangular configuration. The 2 bottom rollers are drive rollers that grip and feed the plate through the machine, while the top roller, which can be adjusted up or down hydraulically, provides the bending force. The beauty of this setup is in its simplicity and efficiency. By varying the top roller pressure and making multiple passes, you can achieve a wide range of diameters and even create nearly perfect circles. The process itself is mesmerizing to watch. The plate enters between the rollers, and as they rotate, you can literally see the flat material take on curvature. For thicker plates or tighter radii, multiple passes are necessary, with each pass increasing the curvature incrementally. Modern machines can handle impressive specs, plates several inches thick and many feet wide, bending them into cylinders or cones with remarkable precision. The rollers themselves are precision-ground, hardened steel, designed to maintain their shape under enormous loads. This technology represents a perfect marriage of time-tested mechanical principles with modern control systems, creating tools that are simultaneously powerful and precise, capable of forming the steel that builds our world.
Every year, the world produces over 20 million tons of mineral wool, with nearly half of that volume coming from the United States. This is a material capable of withstanding direct flame contact at temperatures of 1,500 degrees Celsius, whilst weighing less than the air trapped inside it. How does solid, heavy volcanic rock, born in the Earth's fire, become a light and fluffy insulator resembling delicate candy floss? How have engineers harnessed fire powerful enough to melt stone, to create silence and warmth in our homes? And most importantly, what secret do these enormous factories hide as they transform tons of dirty industrial waste into a clean and safe product for the future? Watch until the end, because what follows is a fact that will forever change your perception of this remarkable stone fleece.
The mineral wool market in the United States is a colossal, invisible machine, churning billions of pounds. We're talking about an industry worth over 4 billion pounds per year. And according to analysts' forecasts, it's only set to grow. This means that right across the country, from the frozen forests of Minnesota to the scorching deserts of Arizona, more and more builders and homeowners are choosing this rock-based jumper for their walls, roofs, and floors. But the story of this material doesn't begin in a factory. It starts deep within the Earth's crust, in the thunderous heart of a quarry. The foundation of it all is basalt. This is a dark, dense volcanic rock, the very material that forms the ocean floor, and which millions of years ago erupted from volcanic vents. But alongside it comes a rather unexpected partner: slag. This is a byproduct from metallurgical giants, a solidified melt of impurities left behind after steel smelting. Once considered worthless waste and simply carted off to landfills, creating entire man-made mountains, today it's invaluable raw material.
Right then, picture the recipe for this industrial marvel. Take several portions of prime crushed basalt for strength, add a touch of slag to achieve the desired chemical properties, and for eco-friendliness and energy savings, generously season it all with recycled glass and offcuts of old mineral wool. All these stony ingredients arrive at the factory in enormous lorries and get tipped into a giant hopper. And now the real inferno begins, quite literally. From the hopper, this mixture, called the charge, flows continuously into an enormous vertical tower, a cupola furnace, or what's known as a cupola. It's a genuine miniature volcano created by human hands. Here, rather like feeding an insatiable maw, they load our stone mixture in layers, along with coke, a special fuel derived from coal that burns with incredibly high and stable heat. Massive fans, roaring like aircraft turbines, pump thousands of cubic meters of air into the furnace, driving the temperature up to absolutely astronomical levels, 1,500 degrees Celsius.
At such temperatures, the stone hasn't got a chance. It melts, cracks, and transforms into a liquid mass glowing an incandescent white. This river of fire flows out of the furnace along a special channel lined with fire brick. The sight is absolutely mesmerizing. A brilliant, blinding stream of molten stone radiating such intense heat that one simply cannot stand nearby without proper protection. And here, at the exit from this inferno, a genuine miracle occurs. The transformation of heavy, viscous liquid into light, airy fluff. This process is called fiber formation. Have you ever watched candy floss being made? A spinning center where sugar is poured in, and fine threads that fly outwards. The principle here is exactly the same, but instead of sugar, molten stone, and instead of a small machine, a gigantic centrifuge. A thin stream of this stone lava hit several massive disks spinning at tremendous speed, making thousands of revolutions per minute.
When a droplet of molten rock strikes such a disk, the colossal centrifugal force instantly stretches it and flings it aside as an incredibly fine fiber, just a few microns thick. That's 10 times thinner than a human hair. Since this process occurs continuously,
An entire cloud of red-hot stone threads flies off the discs. It resembles a golden, luminous chaos. Billions of these finest fibers, cooling as they fly, transform into a light, wool-like mass. In just a moment, our heavy molten rock has become airy and fluffy. But for now, it's simply a formless cloud that needs to be gathered together. Whilst the fibers are still airborne inside a special chamber, a fine mist of binding agent is sprayed onto them from hundreds of nozzles. This is a special phenol formaldehyde resin that envelops each tiny fiber.
This cloud of glue-soaked fibers flies onwards and enters the settling chamber. At the bottom of this chamber sits a wide moving conveyor with a perforated belt. From beneath the belt, powerful fans extract air, creating a vacuum. This directed airflow pulls the fibers downward and lays them evenly onto the conveyor, forming a thick, fluffy carpet. This already resembles the future insulation, but it's still soft and the glue hasn't hardened yet. The thickness of this carpet is controlled by the conveyor's speed. The slower it moves, the thicker the layer that settles. And now this golden yellow fluffy carpet, reminiscent of a giant Swiss roll, is ready for the final stage, baking. It slowly enters an enormous oven known as a curing chamber. This is a long, multi-level tunnel maintained at a temperature of around 200 degrees Celsius. The purpose of this stage isn't merely to dry the carpet, but to bake the adhesive. Under heat, the resin polymerizes. That is, its molecules cross-link into a robust three-dimensional network, transforming into solid plastic that permanently bonds the stone fibers at their intersection points. It's within this oven that mineral wool acquires its final properties. It becomes resilient, capable of recovering its shape after compression. During this process, the resin often changes color, lending the finished product its characteristic yellowish-brown hue. From the other end of this gigantic toaster oven emerges no longer a loose carpet, but rather a solid, springy mat of specified thickness and density. However, it still remains an endless ribbon. Now it's time to transform it into a marketable product. This hot mat passes through an entire system of cutting tools. Sharp circular saws or powerful blades slice it lengthways and crossways with incredible precision into sheets or rolls of standard dimensions, for instance, 16 or 24 inches wide, so they fit perfectly between the studs of a timber frame house. The edges are trimmed, and now we have the familiar product before us. And here, another bit of magic happens: packaging. The finished mats or rolls are fed onto the packaging line. A special press compresses them, removing nearly all the air. The product's volume can shrink several times over. Then this compressed block is quickly wrapped in robust polythene film and heat-sealed. This is done to save an enormous amount of space during transport and storage. It's rather like a vacuum bag for clothes. Instead of a huge, fluffy roll, we end up with a dense, compact package. And when the builder on site cuts through the film, the mineral wool hisses as it draws in air and, like a spring, expands back to its original size within a matter of seconds. The finished packages are stacked onto pallets by robotic arms, wrapped in stretch film, and forklifts carry them off to the warehouse or straight into the back of a lorry. And so, as yet another lorry rolls out through the factory gates, our journey comes to an end. We followed how ordinary solid rock, having passed through the fiery heart of the furnace, became a high-tech cocoon that would preserve warmth, silence, and safety in someone's home for many decades to come.
Now for the most fascinating bit, the environmental credentials, because this is where mineral wool absolutely smashes expectations. We've already mentioned it's made from rock and slag. Well, here's the thing. On average, modern mineral wool contains 70% recycled materials. Sometimes that figure reaches as high as 90%. Just imagine, 3/4 of your insulation is essentially industrial waste that's been given a second life. We're talking about millions of tons of metallurgical slag that used to simply end up in landfills, now transformed into a high-tech product. It's one of the finest examples of a circular economy, where one industry's waste becomes another's treasure. Manufacturing giants like Rockwool or Owens Corning process so much slag each year you could fill thousands of Olympic-sized swimming pools with it.
But that's not all. The second superpower is acoustics. Due to its dense, chaotic fiber structure, mineral wool is an incredible sound insulator. It doesn't just block sound, it absorbs it. When sound waves enter the material's depth, they're forced to navigate through a labyrinth of billions of stone fibers, losing their energy and fading away. That's precisely why it's beloved not only in residential homes for protection from noisy neighbors, but also in professional recording studios, cinemas, and even between floors to avoid hearing footsteps from above. It's like building a personal silent mode into your walls. And finally, the mystery promised at the beginning. Despite mineral wool appearing soft, each of its fibers is a microscopic stone needle. When working with it, these needles can cause mechanical skin irritation, that very itch. And whilst modern technology has made the fibers safer, this stone fluff will always remind you of its true, hard nature, demanding respect and caution.
Every year, humanity throws away more than 50 billion batteries. That's enough to build a tower all the way to the moon. Mountains of toxic metal and chemicals that could become raw material for new life instead of poisoning the planet. But what happens next to all these power sources? Where do they end up after the charge dies in your phone, laptop, or electric car? Behind the plain doors of an ordinary collection point hides an entire industry of the future. This is a world of giant shredders that grind metal into dust, magnetic separators that sort the invisible, and furnaces reaching temperatures of 3,000 degrees Fahrenheit, hotter than the mouth of a volcano. And here's the best part. By the end of this video, you'll find out what actually happens to the lithium that once lived inside your battery and why this process is called urban mining for 21st century treasures. The path to rebirth doesn't start at the factory, it starts in our hands. Collecting used batteries is a massive logistical operation spanning the entire country. Regular people drop off tiny batteries from phones and laptops into special bins installed at electronics stores and supermarkets. Auto shops, like hospitals for cars, pull out massive battery packs from electric vehicles, hundreds of pounds each. Industrial facilities running heavy machinery turn in their spent power sources by the ton. It's like thousands of streams flowing into one big river. Old batteries from factories and auto shops get hauled in armored trucks to regional collection centers. Here's what's interesting. Modern smart collection containers have sensors that track fill levels in real time. When a container's almost full, it automatically sends a signal to the logistics company, which plans a pickup route. When mountains of collected batteries arrive at the sorting facility, one of the most complex and critical stages begins. Batteries come in dozens of different types. Lithium-ion, like the one in your smartphone, nickel metal hydride from old toys, lead acid from cars. Mixing them during recycling is like mixing sand with sugar. At small collection centers, workers sort batteries by hand, like jewelers, relying on markings and appearance. But at large-scale facilities, technology takes over. Batteries move along conveyor belts under the watch of artificial intelligence. Computer vision systems equipped with X-ray and spectroscopic scanners identify the chemical composition of each battery in fractions of a second. Robotic arms snatch the right types from the stream at lightning speed and sort them into different containers. Despite automation, human oversight remains irreplaceable. Operators, like air traffic controllers, monitor the machines and step in when things get complicated. If a battery has a damaged casing or missing labels, only a human can make the right call. This is especially true for the massive batteries from electric vehicles. These giant blocks, weighing up to half a ton, are dismantled into smaller modules using specialized robots, but the final cell sorting is often done by hand. It's painstaking and dangerous work that demands total focus. At the end of the day, every properly sorted battery isn't just a piece of metal. It's a chance to return the most valuable rare earth elements, like cobalt and lithium, back into the economy, and to reduce the enormous damage caused by mining them in the first place. After sorting, the batteries head to their execution, the shredding floor. They fall into the steel jaws of a giant shredder. This is a true industrial monster, whose hardened steel blades can grind up even the armored casing of an electric vehicle battery. Inside the protected chamber, total metallic chaos unfolds. Deafening roars, grinding, and cracking. Batteries literally torn into tiny pieces. But this process is extremely dangerous. Any energy left in a battery can lead to fire or explosion. To prevent this, engineers developed several brilliant solutions. Before shredding, batteries are often subjected to cryogenic freezing in liquid nitrogen at temperatures of -320 degrees Fahrenheit. This not only makes the metals more brittle, but also completely neutralizes any chemical activity. Some shredders operate in sealed chambers filled with inert gases to eliminate contact with oxygen. The shredded pieces pass through a system of magnetic separators that pull steel, nickel, and cobalt from the stream with incredible precision. But the most valuable thing is the fine black powder that settles in specialized dust collectors. It's known as black mass. Right here in this unremarkable-looking dust lie the real treasures of the 21st century: lithium, cobalt, manganese, and graphite. Plastic residue and traces of electrolytes get washed away with special solutions. Engineers in armored control rooms monitor the process through thick glass, controlling temperature and pressure. If a battery does explode, the system instantly snuffs out the flash, and the process doesn't stop for a second. Once the precious black mass has been extracted from the chaos of shredded batteries, the real alchemy begins. Metals that seemed forever locked inside old batteries are recovered using two main methods: hydrometallurgy and pyrometallurgy. Hydrometallurgy is a process similar to cooking up a complex chemical soup. The black mass is plunged into massive reactors filled with acid solutions, typically sulfuric or hydrochloric acid. With constant stirring and heating, metals, lithium, cobalt, nickel, literally dissolve, transitioning into liquid form. To extract a specific metal from this soup, an ion extraction process is used. Special reagents are added to the solution that selectively bind to only one metal, like a key to a lock. As a result, each metal settles into a separate layer. If hydrometallurgy is delicate chemistry, then pyrometallurgy is the primal force of fire. Here, everything literally burns and melts. The black mass gets loaded into a massive arc furnace, where temperatures reach nearly 3,000 degrees Fahrenheit. At that kind of heat, metals melt, and plastic and other organic remnants simply burn away. The molten mass separates under gravity, like oil and water. Heavier metals, such as cobalt, nickel, and copper, sink to the bottom, forming a valuable alloy. The lighter lithium stays in the top layer, in what's called slag. Then this slag is extracted and processed separately to obtain pure lithium. This method is faster and handles larger volumes, but it's also more energy intensive. After cooling, the extracted metals emerge as the purest ingots, shiny, smooth, and ready for their second life. Cooling after the pyrometallurgical process is just as critical a stage. If you simply let molten metals cool in open air, it can take several days and lead to uneven crystal structure formation, which degrades quality. That's why cooling is always controlled. Ingots might move slowly along a conveyor beneath powerful fans. It's like a giant hairdryer that quickly yet evenly cools the surface. For an even faster process, red-hot ingots can be plunged into massive tanks of water or special cooling fluids. It's an incredible sight, glowing metal hitting water instantly shrouded in clouds of hissing steam. Sometimes they use combined cooling too, air cooling first, then water cooling, to reduce internal stress in the metal. Controlled cooling ensures a uniform metal structure, which is critical for reuse, especially in manufacturing new high-tech batteries. The recovered lithium, now in the form of ultra-pure lithium carbonate, heads back to factories to become the heart of new batteries that'll power electric cars or even your phones. Nickel can become part of super strong alloys for turbines that generate energy from wind, and cobalt becomes an irreplaceable component in complex medical equipment. We're literally closing the loop. Old, discarded batteries give life to new, cutting-edge technologies.
Tossed batteries, they can become a full-blown environmental disaster. First, they're packed with toxic heavy metals that seep into landfills, contaminate soil, poison groundwater, and wreck everything around them. Second, mining new rare earth metals is an incredibly dirty, destructive process that drains natural resources and devastates ecosystems on a massive scale. Recycling tackles both problems at once. And here's the real power move. The more batteries we recycle, the less we depend on unstable raw material supplies from other countries, strengthening our technological independence. Despite lithium's critical importance, only about 1% of this metal gets recycled globally today. The main reason? High costs and complex processes. But right now, researchers around the world are developing new, cheaper technologies that could dramatically change the game in the coming years.
Picture this, a sheet of aluminum, 4 millimeters thick. You can bend it with your bare hands, scratch it with a key, punch through it with a hammer. Now imagine that exact same material is what makes up the wing you're sitting on at 36,000 feet. That wing's carrying 300 tons at 550 miles per hour, and it doesn't break, doesn't bend, doesn't crack, for decades. How does a 4 millimeter sheet transform into a structure you trust with your life? Today we're going behind the scenes at an aircraft manufacturing plant where they press wings and fuselages for passenger jets, and I'm going to show you every single step of that journey. If you're into deep dives like this, hit subscribe and ring that bell so you don't miss new episodes. It all starts in the raw materials warehouse, and the first thing that hits you is the scale. Aluminum sheets and plates are stacked several meters high, each sheet marked with its alloy designation. Aviation doesn't use regular aluminum. They use 2000 and 7000 series alloys, enhanced with copper, zinc, and magnesium. These additions make the metal several times stronger than pure aluminum, while keeping its light weight. Every batch arrives with a passport: chemical composition, mechanical properties, ultrasonic inspection results. If even one parameter falls outside tolerance, the entire roll goes back to the supplier. There's no such thing as good enough here. The cost of a mistake is measured in human lives. From the warehouse, sheets travel to the cutting shop on special carts, with soft padding to prevent surface scratches. Laser and water jet cutters slice blanks from digital templates, each part cut to within tenths of a millimeter. A single wing skin set comprises hundreds of parts in different shapes and thicknesses, and each one has its own unique number in the engineering documentation. Now for the most spectacular part, forming. That flat sheet needs to become a panel with precise curvature, matching the aerodynamic profile of a wing or the roundness of a fuselage. For this, they've got presses that'll take your breath away. The hydraulic stretch press for skin forming. This machine stands as tall as a 3-story building, with force measuring tens of thousands of tons. The aluminum sheet gets clamped along the edges by special grips. A massive steel die, the punch, rises from below with the exact shape of the future panel, and the press slowly, inch by inch, stretches the sheet around this form. The metal stretches, takes on the curvature, and stays that way forever. The sound, a deep, heavy groan of metal that makes the floor vibrate under your feet. The entire pressing cycle takes several minutes, but prepping for one cycle? Hours. Setting up the die, calibrating the force, checking the sheet temperature, because cold aluminum behaves completely differently than warm. For fuselage panels, they use a different method, shot peen forming. It looks almost absurd. They lay a flat sheet on a table and blast it with steel balls about a millimeter in diameter from special nozzles under pressure. The balls hammer the surface at enormous speed, creating thousands of microscopic dents. The top layer of metal stretches while the bottom stays the same, and the sheet starts to curve on its own, like running scissors along a ribbon and watching it curl into a spiral. By controlling the intensity of the bombardment and the impact zone, you can achieve precisely the curvature you need, that signature fuselage roundness. The method seems crude, but the precision is stunning, within tenths of a millimeter on panels several meters long. After forming, each panel gets checked with a laser scanner. The beam sweeps across the entire surface, building a three-dimensional model of the part that's overlaid on the digital reference. The computer highlights deviation zones, and if even a single point falls outside tolerance, the panel goes to scrap or rework. The formed panels aren't wings or fuselage yet. They're just skin, a thin shell that can't handle anything serious on its own. To make it withstand flight loads, internal structural elements are attached from the inside, stringers and frames. Stringers are long profiles running along the structure. They handle tension and compression. Frames are cross-sectional rings that maintain the shape. Together, they form a skeleton to which the skin gets riveted. And this sandwich of shell and framework can now bear enormous loads. And here begins the most painstaking work, riveting. A single wing on a passenger jet has several 100,000 rivets. Each one is made from a special aviation alloy. Each one goes into a drilled hole with precision down to a few thousandths of an inch. Automated riveting machines place up to several thousand rivets an hour. The robot drills the hole, inserts the rivet, bucks it, and immediately checks the force. But there are places the robot can't reach. That's where people work. A riveter with a pneumatic hammer and bucking bar is one of the most respected workers on the aircraft factory floor. While the skin is being made, they fabricate the spars, the main load-bearing beams of the wing. These are the most heavily stressed parts in the entire aircraft. The whole fuselage hangs from them, along with passengers, fuel, and cargo. A spar for a large airliner is a single piece up to 115 feet long, milled from a solid aluminum plate several inches thick. A 5-axis machine removes up to 90% of the original metal, leaving behind a complex landscape of ribs, webs, and flanges. Milling a single spar takes up to 24 hours of continuous operation. The cutting tool follows its programmed path inch by inch, and you can't stop the process because any pause will leave a mark on the surface. From a plate weighing several tons, you get a part that weighs 10 times less but can carry loads of hundreds of tons. The chips don't go to waste. They're collected, pressed into briquettes, and sent back for remelting. When all the parts are ready, assembly begins. The wing is assembled in a special jig, a massive steel frame as long as the wing itself, holding every component in its exact position. First, they install the spars, then the ribs, transverse frames that define the aerodynamic profile, followed by the stringers, and finally, the skin. Panels are fitted and riveted one after another. At every stage, inspectors check gaps, alignment, and rivet tension. The tolerance for panel fit-up is 0.3 of a millimeter. If the gap is larger, the panel comes off and gets refitted. Assembling one wing takes about 2 weeks. The fuselage is built in sections: nose, center, tail, and each is finished completely on its own. Then they're joined into a single tube. The moment of joining is an incredible sight. Two enormous cylinders, several meters in diameter, slowly approach each other on rails, slide together with a gap measured in fractions of a millimeter, and lock in place with thousands of bolts and rivets. After assembly comes sealing. Every seam, every rivet hole in the fuselage gets coated with a special sealant that turns flexible and waterproof when it cures. Without it, at 36,000 feet, where pressure is 4 times lower than at sea level, air would leak through microscopic gaps, making it impossible to keep the cabin pressurized. After sealing, they close up the fuselage and pump in pressure, simulating flight conditions. Sensors all over the body track leaks. If air's seeping out somewhere, they hunt it down, find it, fix it. Only after passing that test does the section get cleared. The wing goes through its own trials. They mount it in a test rig and bend it upward with hydraulic cylinders, slowly, carefully, measuring deflection at hundreds of points simultaneously. The wing has to withstand bending several feet upward without breaking. It flexes like a bow, but doesn't snap. During certification tests, they bend the wings until they actually break to know the exact failure limit and confirm it exceeds the design spec with margin to spare. Once the wing and fuselage pass every inspection, they're hauled to final assembly. That massive hangar the size of several football fields, where ceilings soar 10 stories high. Here, wings mate with the fuselage through the central keel beam. Landing gear gets installed, engines hang beneath, cockpit and systems go in. From separate sections, an airplane is born. The entire journey from flat sheet aluminum to finished wing, that's months of work, hundreds of operations, millions of control points. Every rivet recorded in a passport, every seam documented, every panel with its own story, from metal smelting to the machine number that formed it. Next time you sit by the window and look at that wing, remember, this structure started as a flat sheet barely 1/6 of an inch thick. And every fraction of that journey, someone's work, someone's inspection, someone's craft.
What if I told you that inside the most dangerous machines on the planet lies a steel secret that can only be created once? And a single mistake costs an entire nation. That there's an ingot that cools underground for 6 weeks and withstands pressure that would crush mountains? This giant is born in fires exceeding 2,700 degrees Fahrenheit, endures months of forging, strikes of tens of thousands of tons, and thermal shocks that would blow ordinary metal to bits. In 2015, a British company, Sheffield Forgemasters, poured 607 tons of molten steel into a giant casting pit. That's nearly the weight of a full passenger Airbus A380. After cooling, the ingot weighed 320 tons. To forge these giants, they use presses with a force of up to 40,000 tons. The energy for heat treating ingots over a 2-week cycle can exceed 100,000 kilowatt hours. That's the annual consumption of dozens of ordinary households. Stick around till the end. You'll find out what these monoliths are actually made for and why. Without them, the modern world would simply grind to a halt. Picture a massive foundry floor at a steel mill. This is where it all begins. To get a monolithic ingot, you need liquid steel of flawless quality, poured into a mold in one continuous stream. This stage demands maximum coordination. We're talking thousands of degrees and hundreds of tons of metal. A striking example of such an engineering feat was the record pour carried out by the British firm Sheffield Forgemasters in 2015. The company's metallurgists successfully managed the casting of 607 tons of liquid steel into a giant casting pit. To put that volume in perspective, it's nearly the weight of a full-sized Airbus A380 passenger jet. The pouring process is critically important. The steel must not only be melted but also purified to a level meeting the strictest customer requirements, for reactor components, for instance. That means minimizing impurities, gases, and slag. Continuous casting ensures there won't be any layered defects or boundaries in the ingot structure that would compromise its mechanical strength. During casting, the steel must be degassed as much as possible. Oxygen and nitrogen content is controlled at levels that often don't exceed 20 parts per million. Excess gases can cause microvoids to form inside the monolith during cooling. Right after pouring the liquid metal, which can exceed 2,700 degrees Fahrenheit, time becomes the critical factor in this process. Unlike small castings that can be cooled quickly, a steel giant weighing hundreds of tons cannot be cooled rapidly. If cooling happens too fast, it'll lead to massive internal stresses, cracks, and structural defects, because the outer layer will solidify while the interior is still liquid. To ensure uniformity in the crystalline structure, the 607-ton ingot was left to cool in the casting pit for 6 weeks. This is a controlled, extremely slow process during which the steel gradually solidifies, dropping to a temperature of around 2,000 degrees. This slow crystallization allows the metal to avoid unwanted phase transformations and guarantees high-quality macrostructure, which is the foundation for the future component's strength. Only after this lengthy solidification period ends is the steel monolith, which, after shrinkage and removal of the defective top portion, weighs roughly 320 tons, carefully extracted from the ground. The ingot pulled from the earth, despite its weight, is not yet a finished blank. It has a cast, coarse structure with large crystals. To transform it into strong, homogeneous metal capable of withstanding extreme loads, forging is needed. Forging 500-ton ingots requires hydraulic presses with working forces from 10 to 20,000 tons. For instance, forging the largest reactor components uses presses rated at 40,000 tons. Before forging, the ingot is again carefully heated in special furnaces. This process can take weeks to ensure uniform heating throughout the entire volume of metal. The forging itself happens on giant hydraulic presses capable of generating tens of thousands of tons of pressure. The press breaks up large, brittle cast crystals. The pressure compresses the metal, eliminating microscopic voids that may have formed during casting. The metal develops a directional fibrous structure, significantly increasing its strength, toughness, and fatigue resistance. The forging process for such an ingot takes several months. It's a constant cycle of heating, pressing, rotating, and reheating. Every press stroke is a precise calculation aimed at achieving the required internal geometry and mechanical properties. The energy needed to maintain the heat treatment furnace for ingots during a 2-week cycle can exceed 100,000 kilowatt-hours. That's comparable to the annual electricity consumption of dozens of typical households. During heat treatment, the allowable temperature variation throughout the furnace can be just 70 degrees Fahrenheit, which requires highly precise multi-zone control systems. After shaping the ingot comes heat treatment. This is the final, critically important stage for tuning the internal structure of the steel. The multi-ton steel monolith, which just endured months of casting and forging, is like a clumsy giant whose final character hasn't yet formed. It's strong, but its internal structure is still chaotic, full of invisible internal stresses. The first stage is normalization, or as they say, homogenization. The idea is simple. We essentially stir the metal structure so it becomes absolutely uniform throughout its entire volume. This is done so that at every point in the blank, both at the surface and deep inside, the steel has identical properties. It's like evening out the temperature in an oven so the cake bakes perfectly. Then comes the most dramatic moment, quenching. The blank is heated to very high temperature, bringing it to peak plasticity. And then, suddenly, but under strict control, it's cooled. This could be a water or oil bath. This nature shock transforms steel's soft structure into the hardest, strongest form possible. It gives the part its core fighting power, but there's one side effect. The metal becomes brittle, like glass, and massive internal stresses appear. If you leave it like that, it could crack from the slightest impact. That's why the final and most humane stage is tempering. The blank gets carefully reheated, but this time to a significantly lower temperature. The goal isn't to change the strength, it's to release those internal stresses that built up during rapid quenching. Think of it like a deep exhale after stress. It boosts the steel's toughness, making it impact-resistant and load-bearing, eliminating the brittleness. Only after successfully completing this full month-and-a-half cycle of character hardening is the steel ready to become part of a reactor or a giant press. But what are these steel giants actually for? These things we've invested so much time and resources into. They become critically important components in industries where the cost of failure is unacceptably high. Take nuclear power, for instance. These ingots become critical components in high-pressure reactors. Picture this. Pressure, temperature, and radiation demand absolute reliability. No seams, no welded joints that might fail. Just one solid monolith capable of handling extreme stress for decades. In heavy machinery, these giants become bed frames for the world's largest presses. These presses shape automotive frames, aircraft parts, and ship components. A bed frame that won't deform under thousands of tons of load, it has to be cast in one piece. And then there's power generation. Rotors for massive steam turbines or crankshafts for enormous marine engines that propel supertankers and container ships. These components need guaranteed resistance to bending and secondary loads. Only steel produced through this incredibly complex process can deliver that. And just like that, after pouring 607 tons of molten steel at 2,700 degrees Fahrenheit, through 6 weeks of slow underground cooling, through shrinkage down to 320 tons, through months of forging under 40,000-ton presses, through strikes of tens of thousands of tons, through normalizing, quenching, and tempering over 6 weeks, through consuming 100,000 kilowatt-hours of energy, a steel monolith is born, a single seamless giant capable of withstanding pressure that crushes mountains, temperatures that melt ordinary metal, and radiation that destroys all living things. This monolith becomes the heart of a nuclear reactor, the bed of a giant press, or the rotor of a turbine driving a supertanker. Without these steel giants, nuclear power plants would grind to a halt, ship engines would fall silent, and aircraft parts production would cease. Each ingot like this isn't just a chunk of metal. It's the result of incredible engineering precision, months of painstaking work, and millions of dollars in investment. And mistakes here are unacceptable, because the price could be too high for an entire nation.
What if I told you the world's toughest roads and roofs aren't born on the construction site, but deep inside oil's blazing heart. A material that survives 360-degree heat and brutal cold. One mistake by the technologist, it turns to stone. But why did this black, sticky residue at the bottom of the oil column become the backbone of bridges, airfields, and massive warehouses? And what chemical secret lets it survive for decades without cracking under 40-ton trucks? Every year, the world produces hundreds of millions of tons of bitumen. It's extracted at temperatures between 930 and 1200 degrees Fahrenheit, squeezing literally the last drops from crude oil. Roofing felt? It passes through vats of molten bitumen at 570 degrees, where every inch of cardboard or fiberglass gets soaked in black gold. One wrong step in the process, and within a couple winters, that road's covered in ruts and potholes. Stick around till the end. You'll discover what even some manufacturers won't tell you.
Picture a massive oil refinery. Giant distillation towers, tall as a 20-story building. Crude oil flows in and gets heated to 650 to 750 degrees Fahrenheit. Fractional distillation begins. Light fractions, gasoline, kerosene, vaporize and rise upward. Middle fractions, diesel, fuel oil, remain in the center. And at the bottom of the tower, a heavy tail accumulates, thick, dark residue. This isn't bitumen yet, but it's already the base for it. This residue goes to a vacuum column. There, it's heated again, but under vacuum, at reduced pressure. This allows even more fractions to evaporate, which become lubricating oils and paraffins, without pushing the temperature high enough to break down the heavy molecules. What remains after this squeezing out of the heaviest parts, that's the foundation for bitumen and tars. But it's still a raw product. Next, chemistry kicks in. Into enormous reactors, they load this residue and add other components. For example, light oils, polymers, modifiers, sometimes sulfur.
At temperatures between 500 and 650 degrees, the mixture is held so large organic molecules partially cross-link, becoming more viscous and heat-resistant. Complex chemical reactions occur: oxidation, polymerization, condensation. Hydrocarbon molecules unite into even larger and heavier structures. The result is a thick, extremely sticky material that becomes solid or glass-like when cooled. It can be crushed into chunks, dissolved in organic solvents, or heated to a liquid state and applied as a waterproofing layer. Bitumen is a close cousin of tar, but with a clear focus on road construction and roofing. It's also derived from heavy petroleum residues after vacuum distillation. In large bitumen plants, it's less about pure chemistry and more about fine-tuning viscosity and temperature behavior. If the bitumen is too hard, it'll crack in winter. If it's too soft, it'll run in the heat at 200 degrees on the asphalt.
That's why the technology has a concept called penetration, how deep a needle enters a sample at a given temperature and load. Engineers tweak the ratio of light and heavy fractions, add polymer modifiers to get a material that won't flow in the heat and won't turn brittle in the cold. In massive mixers, bitumen is heated to temperatures from 450 to 650 degrees Fahrenheit, and under intense mixing, they add modifiers, mineral powder, sometimes acidic or alkaline additives to stabilize the structure. That's how polymer-modified bitumens are born, for high-performance roads, airfields, bridge expansion joints. When people say asphalt road, they actually mean a mix of mineral materials, crushed stone, sand, mineral powder, with bitumen as the binder. In huge asphalt mixers, the crushed stone is pre-dried and heated to temperatures close to 570 degrees Fahrenheit to ensure there's no moisture.
Then hot bitumen gets added and mixed until every single pebble is coated in a thin film of binder.
The hot mix heads into dump trucks, then straight to the job site for paving. Get the bitumen wrong? A few seasons later, you're looking at ruts, cracks, and potholes. Nail the process? That pavement will handle years of trucks weighing dozens of tons. Roofing felt. It's the story of turning a simple roll of backing into a durable shield against rain, UV rays, and temperature swings. The base is cardboard, fiberglass cloth, or a polyester mesh in roll form, roughly 3 feet wide. Cardboard backing gets picked for budget materials and light-duty jobs, fiberglass when you need better heat resistance and less warping, and polyester for flexible roofs where stretch and tear resistance matter. All these backings share one trait: they're porous, so without treatment they soak up water easily and fall apart fast. To turn a bare base into waterproofing material, the roll gets run through a processing line with vats of hot bitumen or bitumen resin compounds. The liquid bitumen is heated to a range of 450 to 570 degrees Fahrenheit, sometimes higher, to lower viscosity and ensure quality penetration into the fibers. The roll is fed on rollers into the vat so that it's completely submerged in the melt and passes through at a controlled speed. During this time, bitumen fills the pores of the cardboard or fabric, displaces air and moisture, forming something like a skeleton flooded with waterproof mass. After exiting the vat, excess material is removed by calibrating rollers. This helps maintain the specified thickness and avoid drips. Next comes the stage of forming the coating layers. The saturated base passes under bitumen or resin applicators that apply the main layer on the bottom and top. For this, knife or roller coaters are used. A thin gap between the roller and support measures out the coating thickness. The bottom layer handles adhesion to the roof deck or foundation, so it can contain more elastic plasticizers, polymers, oils, special additives that reduce the risk of cracking during bending and temperature swings. The top layer acts as armor against sun, rain, hail, and physical damage, so it's made harder and more heat resistant, sometimes modified with polymers for better UV resistance. While the top layer is still hot and sticky, it gets coated with mineral granules. A dispenser on the line drops a steady stream of mica, basalt granules, or slate onto the moving belt. The particles instantly press into the soft bitumen and lock in place as it cools. This coating isn't just for nice rough texture, it works as a shield against ultraviolet radiation. The sun heats the exposed bitumen surface less, the material ages slower and doesn't crack as fast. Plus, the granules boost abrasion resistance. After the granules are applied, the sheet moves through a cooling zone. This uses either air cooling or systems with water baths and chilled rollers that pull heat away from the hot bitumen. It's crucial that the temperature drops to a safe level before winding into rolls. If you roll up hot material, the layers stick together, the geometry gets thrown off, and the granules can lose adhesion. To monitor parameters on the line, they install temperature sensors and thickness gauges that ensure the coating layer doesn't come out too thin or too thick. A thin layer means future leaks. Too thick means wasted bitumen and problems during rolling and installation. The next stage is cutting and winding. The roofing felt sheet is cut lengthwise or crosswise into standard rolls, most often between 30 and 50 feet long. Each roll is tightly wound onto a core, so the edges don't shift and the upper layers don't slip. Sometimes one side is left with a strip without granules, covered with pure bitumen. When laying, this strip gets overlapped by the adjacent sheet, forming a watertight seam that film or granules won't stop you from heating with a torch. Polyethylene or paper liners get added to the roll so the layers don't stick together during shipping and storage. The finished material gets labeled. The tag shows the type of base, the weight of bitumen per square yard, the type of surfacing, the flexibility temperature, and other specs that matter to designers and installers. The story doesn't end there though, because how roofing felt behaves on a roof depends heavily on what exactly got mixed into it back at the factory. If you take regular oxidized bitumen, the material will be cheap but sensitive to temperature swings. On a sunny roof, where the surface easily heats up to 360 degrees in summer, that layer gradually loses elasticity, becomes hard and brittle. To prevent that, polymers get added to the binder. Polymer modifiers make the material more flexible in cold weather and better at handling high heat.
Roll roofing can easily withstand both winter freezes and summer scorching without developing a spiderweb of cracks. It's polymer modifiers that gave Roofoo Felt new life in the competition with membrane roofing systems. Picture a warehouse complex roof spanning several 100,000 square feet. The classic setup: leveled substrate, a layer of primer from bitumen emulsion, then several layers of roll material with a 4-inch overlap. The bottom layer is often torch applied. You flip it granule side up, heat it with a gas torch until the bitumen softens, and roll it onto the substrate. The top layer goes down the same way, forming a continuous blanket, where the seams are the most critical zones. The quality of that seam determines whether the roof leaks or not. And so, traveling from the bottom of an oil column, through vacuum distillation, through heating to 1200 degrees and oxidation, through vats of molten bitumen at 570 degrees, through coating with mineral granules and cooling, a material is born that protects millions of buildings from rain and snow, withstands 356 degrees of heat and minus 22 degrees of cold, serving for decades without a single crack.
Imagine a part so perfect it can spin for 30 years without stopping. From tiny balls just 1/8 of an inch across to giants 30 feet tall holding up wind turbines, bearings are a $120 billion a year industry. But their life begins in absolute chaos. Massive explosions, hellish fire, pressure that could crush a tank. How does raw metal become the heart of perfection? Today you'll follow the complete journey, from a quarry blast to the perfect ball spinning at 10,000 revolutions per minute. If you want to see how chaos turns into precision, subscribe to the channel. Here we show the manufacturing that builds our world. It all starts with a roar that shakes the ground for miles around. In the giant quarries of Australia and Brazil, iron ore hides in layers of rock hundreds of feet thick. Geologists turn the quarry into a chessboard. They drill boreholes 60 to 100 feet deep. Borehole diameter, 10 inches. Distance between boreholes, 16 feet. 1 square mile, 1,000 boreholes. Into each they pour explosives, a mix of ammonium nitrate and diesel fuel. Ratio 94 to 6%. Charge weight per borehole, 650 pounds. Detonation happens with millisecond delays. First borehole explodes. 20 milliseconds later, the second. 40 milliseconds, the third. The wave rolls across the entire field. In 10 seconds, they detonate 200 boreholes. They blast 3.5 million cubic feet of rock, energy equivalent to 110,000 pounds of TNT. But this isn't random chaos. This is planned destruction. Chunks of rock shoot 150 feet into the air. They fall. Dust rises over half a mile into the sky. When it settles, instead of a mountain, there lies 2 million tons of crushed ore. Giant excavators roll onto the site. The excavator bucket? 1,400 cubic feet. That's the volume of a small apartment. The bucket weighs 28 tons. One scoop? 100 tons of rock. They load it into dump trucks. Hauling capacity of each truck, 360 tons. Wheel height, 13 feet. Diameter, 11.5 feet. Weight of one wheel, 5 tons. Engine, 3,500 horsepower. Fuel consumption, 35 gallons per mile. The dump truck hauls ore to the crusher. Distance, 9 miles. Speed, 25 miles per hour. Travel time, 20 minutes. In one day, a single truck makes 30 trips, hauls 10,000 tons. 20 excavators and 60 dump trucks work the quarry. They move 300,000 tons of ore per day. That's 100 million tons a year. Crushing. Ore enters the jaw crusher. The crusher's mouth, 13 feet wide. The jaw weighs 120 tons. Jaw stroke, 12 inches. Oscillation frequency, 200 strikes per minute. Drive power, 1.5 megawatts. The crusher pulverizes yard-wide rocks into 8-inch chunks. Throughput, 2,000 tons per hour. From the jaw crusher, ore moves to the cone crusher. The cone spins inside the bowl at 150 revolutions per minute. Gap between cone and bowl, 1 inch. 8-inch pieces become 1-inch pieces. Then the ball mill. Cylinder 20 feet in diameter. Length 26 feet. Inside steel balls. Ball diameter 4 inches. Weight per ball 9 pounds. Total balls 50,000. Combined weight 200 tons. The mill rotates at 18 revolutions per minute. Balls drop from 6.5 feet. Impact grinds ore to powder. Particle size after milling 0.04 inches. The thickness of a human hair. Thickness. Flotation enrichment. Ore powder gets mixed with water, creates a slurry. Solid concentration, 30%. Add reagents. Potassium xanthate, 7 ounces per ton of ore. Pine oil, 1.8 ounces per ton. Xanthate makes iron particles hydrophobic. They repel water. Pour the slurry into the flotation machine. Tank volume, 13,000 gallons. Air pumps in from below. Pressure, 30 pounds per square inch. Flow rate, 10,000 cubic feet per hour. Air forms billions of bubbles 0.2 inches across. Bubbles stick to iron particles. Lift them up. Foam forms on the surface. Reddish gray. Dense. Iron content in the foam, 67%. Waste rock sinks to the bottom. Gets pumped out and dumped in tailings. Foam scraped off with blades, sent to filtration. Vacuum filter sucks out the water. Leaves a damp mass. Moisture content, 9%. That's concentrate. Gets turned into pellets. Pelletizing. The concentrate goes to a disc pelletizer. The disc is 15 feet across, tilted at 45 degrees, spins at 15 revolutions per minute. Powder feeds onto the disc. Water's added, 3% by weight. Centrifugal force rolls the powder into balls. Pellets come out 1/2 inch in diameter, give or take 1/16 of an inch. The pellets roll off the edge onto a conveyor. Output? 300 tons an hour. 1 million pellets every hour. The pellets head to the kiln. Firing temperature, 2,450 degrees Fahrenheit. 20 minutes in the heat. The pellets turn rock hard. Crushing strength, 3,500 psi. Now they're ready for the blast furnace. Blast furnace smelting. Pellets are loaded into the blast furnace. The furnace stands 105 feet tall. The throat diameter, 40 feet. The hearth diameter, 26 feet. Furnace volume, 42,000 cubic feet. Loaded in layers. Pellet layer, 3 feet. Coke layer, 20 inches. Limestone layer, 8 inches. Hot air blasts in from below. Temperature, 2,200 degrees. Pressure, 60 pounds per square inch. Flow rate, 100,000 cubic feet per minute. The coke burns, carbon monoxide releases. It strips the iron from the pellets. Temperature in the hearth, 3600 degrees. The iron melts, flows downward, pools in the hearth. Every 4 hours they tap the pig iron. They open the tap hole. Pig iron pours out like a river of fire. Temperature at 2700 degrees. Color, bright orange. One tap, 300 tons. In 24 hours, the furnace produces 2,000 tons of pig iron. The pig iron contains 4% carbon. That's way too much. Pig iron's brittle. Needs converter smelting. Steel production. They pour pig iron into an oxygen converter. The converter holds 350 tons. A lance descends from above. The lance is 20 inches across. Pure oxygen blasts through the lance. Pressure hits 175 pounds per square inch. Flow rate, 18,000 cubic feet per minute. Jet velocity, 1,300 miles per hour. That's twice the speed of sound. Oxygen oxidizes the carbon burns. Turns into carbon dioxide. Flame shoots out the converter's mouth. Flame reaches 30 feet high. Temperature hits 3,600 degrees. The process takes 20 minutes. Carbon content drops from 4% down to 0.7%. This is bearing steel. Grade designation SAE 52100. Chromium content 1.5%. Chromium provides hardness and wear resistance. They pour the steel into a ladle, from the ladle into molds. Out come ingots, blanks weighing 5 tons each. Ingot dimensions 3 feet by 3 feet by 6 feet. Rolling and machining. Ingots are heated in a furnace to 2,200 degrees Fahrenheit. Rolled on a mill. Rollers 40 inches in diameter. Rolling force 2,000 tons. The ingot becomes rods 4 inches across. Rod length 20 feet. Rods are cut into blanks 8 inches long. Blanks are heated to 1,560 degrees. Stamped into rings on a press generating 1,200 tons of force. You get a ring with an outer diameter of 4 inches. Inner diameter, 3.1 inches. Height, 0.8 inches. Rings undergo heat treatment. Heated to 1,540 degrees. Held 30 minutes. Quenched in oil at 140 degrees. Cooling rate, 540 degrees per second. Tempered at 360 degrees for 2 hours. Hardness after heat treatment, 62 Rockwell. Then, grinding. The ring is clamped in a lathe chuck. The abrasive wheel spins at 100 feet per second. Removes a metal layer 0.004 inches thick per pass. Surface roughness, 0.08 millionths of an inch. That's 10 times smoother than glass. Deviation from roundness, no more than 0.08 thousandths of an inch. Balls are made by cold heading. Wire 1/2 inch in diameter is cut into 1/2 inch segments. Each segment is clamped between 2 dies. Pressure, 2 tons. The segment deforms into a sphere. You get a rough ball? It's ground between 2 cast iron discs. The discs rotate toward each other. Speed, 200 revolutions per minute. Between the discs, abrasive paste. Grit size, 40 micrometers. Grinding takes an hour. The ball shrinks by 0.012 inches. Final diameter, 0.46 inches. Deviation, plus or minus 0.004 hundredths of an inch. Sphericity, 0.08 thousandths. Roughness, 0.02 millionths of an inch. Bearing assembly. Inner ring, outer ring, 17 balls. Brass separator, lithium grease. Bearings done. It'll spin for 30 years, 1 billion revolutions.
Every year, aircraft around the world cover more than 25 billion miles. That's roughly 26,000 trips around the Earth. And it's all thanks to the heart of aviation, the turbofan engine. Inside, there's a genuine inferno where temperatures reach over 1,100 degrees Celsius. But how can a machine made of metal survive where steel melts? How do they craft blades with micron-level precision that spin faster than a bullet? And why are some components today literally grown from powder using lasers? Stay with me till the end, and you'll discover a secret that'll forever change how you think about engineering. Turbofan engines that power the giants of the sky, Boeing and Airbus aircraft, seem like something out of science fiction. Yet they're the genuine embodiment of engineering brilliance. How do you assemble these remarkable machines from tens of thousands of parts and materials like pieces of a puzzle? Ordinary metals simply won't do for their manufacture. The engine must operate in conditions where temperatures can exceed 1,100 degrees Celsius. It's a proper inferno, and ordinary steel simply wouldn't cope. This is where titanium alloys enter the picture. Lightweight, robust, and capable of resisting melting in extreme heat. And for the hottest zones of the engine, they use nickel-based superalloys. Such extreme temperatures arise from the fuel combustion process in the combustion chamber. During engine operation, aviation fuel, typically kerosene, mixes with air and ignites, creating hot gases. These gases literally accelerate to extraordinary speeds and temperatures, over 1,100 degrees Celsius, sometimes reaching 1,500 in modern engines. This level of heat is essential to achieve maximum efficient thrust. That is, the hotter and faster the gases, the stronger the energy flow that drives the turbine and propels the aircraft. Here lies the principal challenge. The engine must not only withstand these extreme conditions, but also operate reliably. You know what's remarkable about the engine manufacturing process? Even individual components, such as turbine blades, are crafted with micron-level precision. For instance, blades are cast in a vacuum to ensure there isn't even the slightest crack inside. Some are formed to have a single crystal structure, meaning the metal has not a single seam. But that's not all. Three-dimensional printing? Yes, that's used too. For instance, for complex components that are impossible to create through traditional casting. Turbine blades are the engine's heart. They operate in the hottest zone and convert the energy from hot gases into rotational movement. First, a blade model is created from wax. Then the show begins. In a special furnace, superalloys are melted, composed of nickel, chromium, and other metals capable of withstanding temperatures above 1,100 degrees. This molten metal is poured into a ceramic mold. But the secret lies not only in the material, but also in how it's done. To ensure the blade withstands tremendous temperatures and stresses, it's often cast as a single crystal. This means the entire piece of metal has no seams or micro cracks. Why does this matter? Seams or micro cracks in such conditions are like a minefield. One error and the blade fails. Single crystals are grown through very gradual cooling. Once the metal cools, the ceramic mold is broken away and the blade undergoes thorough grinding. A special heat-resistant coating may be applied to the surface. And so, each blade is inspected individually. If there's even the slightest defect, it doesn't proceed further. Fuel injectors, combustion chamber components, or even compressor blades in aviation are manufactured using three-dimensional printing. For instance, GE Aviation prints injectors for their engines that weigh 25% less but are 5 times stronger than traditional ones. Layer by layer, from powder and light, components are created that allow aircraft to fly faster, further, and more efficiently. First, engineers create a digital three-dimensional model of the component with maximum precision. Here, every curved surface or cavity matters. Why? Because these components often operate in places where a millimeter can change everything, from engine efficiency to its reliability. Instead of the usual chunk of metal, they use ultrafine powder here, for instance from titanium, nickel, or Inconel. It resembles sand, but with particles so minute they're barely visible to the naked eye. The powder is poured into a special reservoir and it becomes the building material. The printer's working principle is straightforward yet brilliant. It melts the powder using a laser or electron beam. The laser heats the powder to such a temperature that it literally fuses into a uniform metallic structure. Then the next layer of powder is applied and the process repeats. This method is called selective laser sintering or melting. And here's what's splendid. Three-dimensional printing allows the creation of even the most complex geometrical forms. For instance, components with internal cooling channels that simply cannot be manufactured through casting or milling. You see, in traditional manufacturing, you often need to create a large component first, then cut away everything superfluous. The resulting component isn't quite ready yet. After printing, it undergoes heat treatment, heated and gradually cooled to relieve internal stresses in the metal. Then comes final grinding, polishing, or mechanical processing if precision needs correcting. And naturally, each component passes rigorous testing. After all, this is serious business. If a component can't bear the load, the consequences could be catastrophic. Engine assembly takes place in an enormous hangar, where every square foot is occupied by tools, engine parts, and people in overalls. Everything begins with the engine casing, resembling a gigantic metal cylinder. This is the skeleton to which all other parts will be attached. The casing is crafted from titanium or nickel alloys, as it must withstand tremendous loads. Engineers work like watchmakers. The casing is secured in an enormous machine to ensure everything is absolutely straight. Next come the compressors, several rows of blades responsible for compressing air before feeding it into the combustion chamber. Blades are installed one after another. Each is inspected manually. Following the compressors comes the turbine stern. Next, the combustion chamber is installed, the engine's genuine inferno. Here, compressed air mixes with fuel and burns. Engineers install special injectors that ensure uniform fuel delivery. And here, everything must be perfect. An incorrect injector angle, and the engine could lose efficiency or even fail. Running through the entire engine is a central shaft, a sort of backbone. At one end of the shaft, the fan is mounted in the form of an enormous wheel at the engine's front, whilst at the other end sits the turbine. To install the shaft, they employ special robots. Once the engine's internal section is assembled, external systems are added. Fuel pipes delivering combustion to the combustion chamber. The oil system, ensuring lubrication of all moving parts. And electronics, because the engine is literally packed with sensors monitoring temperature, pressure, revolutions, and much more. These elements are secured using cables, tubes, and bolts that must withstand not only vibration, but also extreme temperatures. After assembly is completed, the engine isn't dispatched to an aircraft straight away. First, it's mounted to a test stand where real flight conditions are simulated. Once the engine passes all tests, it's disassembled, the principal components are inspected once more, and then it's assembled definitively. The finished engine is packaged and transported to a Boeing or Airbus factory where it becomes part of a new aircraft. So there you have it. Component by component, engineers create the aircraft's heart, capable of carrying thousands of passengers across continents. Isn't that a modern masterpiece? Do write and let me know if you'd like to see more videos like this.
Picture a metal lighter than plastic, burns brighter than the sun itself, and you can pull it straight from seawater. Sound like science fiction? This is magnesium, the metal that revolutionized aviation, space exploration, and even your smartphone. Every year, humanity produces over 1,200,000 tons of this remarkable material. But few people know that behind an ordinary chunk of silvery metal lies technology worthy of science fiction. How does material stronger than steel and lighter than aluminum emerge from ordinary seawater or rock? You'll discover why magnesium burns at temperatures reaching 3,000 degrees, how it's extracted from the ocean floor, and why no modern aircraft can exist without it. Watch until the end. The finale will transform your understanding of what lightness and strength really mean. This is the story of the metal of the future, already here. The story of magnesium began in 1788 in a small English town called Epsom. A local farmer named Henry Wicker noticed something odd. His cows refused to drink water from a particular well. The water was bitter, but it had an amazing property. It healed. People from all around started coming to this spring. That's how a mineral was discovered, later named Epsom salt or magnesia. But this was just the beginning. Pure metallic magnesium was first produced by British chemist Humphrey Davy in 1808 through electrolysis. He passed an electric current through molten magnesium salt and got silvery drops of a previously unknown metal. The metal turned out to be remarkable. It was incredibly light yet strong, and most astonishing, it burned with a blinding white flame, brighter than any material known at the time. In the 19th century, magnesium was rarer than gold. Scientists produced it by the gram in laboratories for experiments. Everything changed when inventors realized something. Magnesium could create brilliant light. Early photographers fell in love with this metal. A flash of magnesium powder delivered such powerful light that you could take pictures even in total darkness. Picture this. The 19th century, a dark studio. A photographer ignites a pinch of magnesium powder and boom! A blinding flash illuminates everything around. That's exactly where the expression magnesium flash came from. But the real breakthrough happened in the 20th century when humanity mastered mass production. Magnesium turned out to be the ideal material for aviation. Lightweight, strong, easy to machine. During World War II, magnesium production skyrocketed tenfold. Military aircraft needed lightweight and durable parts, and magnesium became a strategic material on par with oil and steel. But where does this amazing metal come from? Magnesium is one of the most abundant elements on Earth. It's the 8th most common in the Earth's crust. But you won't find it in pure form. It's too chemically active and always bonded with other elements. The main sources of magnesium are dolomite and magnesite, rocks extracted through open pit mining. The largest deposits are in China, Russia, Turkey, and North Korea. But there's another source, practically inexhaustible: the ocean. Every cubic mile of seawater contains about 3 million tons of magnesium. Imagine the scale. The world's oceans hold roughly 4 quadrillion tons of magnesium. That's enough to last thousands of years even at current consumption rates. That's exactly why many modern plants are built right on the coast. Why dig in the ground when you can draw from the ocean? Now let's dive into the actual production. There are 2 main methods for obtaining magnesium: thermal and electrolytic. Let's start with the thermal method, which is used when the raw material is dolomite or magnesite from quarries. First, the rock is crushed into small pieces, no bigger than a walnut. Then these pieces go into huge rotating kilns. Picture a steel cylinder the length of a football field, slowly turning. Inside, temperatures hit over 1800 degrees Fahrenheit. At that temperature, carbon dioxide burns off from the dolomite, leaving magnesium oxide, a white powder that looks like chalk. This powder gets mixed with coke and silicon, then pressed into brick-sized briquettes. These briquettes are loaded into special retorts, sealed steel vessels that can withstand extreme conditions. That's where things get really interesting. The retorts are placed into massive furnaces and heated to 2,200 degrees Fahrenheit. At this temperature, the chemical reaction begins. Silicon displaces magnesium from its compounds. But there's a problem. At this temperature, magnesium turns into vapor. Yeah, you heard that right. The metal evaporates, just like water in a kettle. The magnesium vapor rises up through the retort and enters a condenser, a specially cooled chamber. Here, the temperature drops sharply and the magnesium vapor condenses. Crystals of pure metallic magnesium grow on the cold walls. It's like frost on a window, except instead of ice, it's silvery metal. The process happens in a vacuum or in an inert gas atmosphere. Because magnesium is so reactive, it can ignite even in regular air at high temperatures. After several hours, they open the retort. Inside, an ingot of pure magnesium weighing about 22 pounds. It's warm, silvery, covered with a thin oxide film. Now let's break down the electrolytic method. This is exactly what they use when extracting magnesium from seawater. The process starts right on the ocean shore. Seawater gets pumped into massive tanks and treated with lime. The lime reacts with magnesium salts dissolved in the water, forming a white precipitate, magnesium hydroxide. This precipitate settles to the bottom. They collect it and rinse it. You get a white paste that looks like toothpaste. They treat this paste with hydrochloric acid, producing magnesium chloride, a clear solution with a bitter taste. The solution gets evaporated in enormous vats, yielding magnesium chloride crystals, white like coarse salt. These crystals are the key to obtaining pure metal. They load them into electrolytic cells, massive steel containers lined with refractory brick. Inside, molten magnesium chloride at 1300 degrees Fahrenheit glows orange like volcanic lava. A powerful electric current flows through the molten salt, thousands of amps. The magic of electrolysis begins. At the cathode, the negative electrode, droplets of pure magnesium form. They float to the surface because magnesium is lighter than the salt it's extracted from. A layer of liquid metal forms on top, which workers periodically collect with a special ladle. Picture this: a ladle scooping silvery liquid from the surface of a glowing orange melt. It's like skimming cream off milk, except the cream is molten metal at 1200 degrees Fahrenheit. The magnesium is poured into molds and left to cool. You get ingots weighing between 11 and 33 pounds each. They're silvery, lightweight. You can lift a 33-pound ingot with one hand. The surface quickly forms a thin oxide film that protects the metal from further oxidation. Without this film, magnesium would slowly oxidize even in air. Now we've got pure magnesium, But what do we do with it? The applications are vast, and all of them are impressive. Let's start with aviation and aerospace. Magnesium and its alloys are used to make aircraft fuselages, engine components, landing gear. Why? Because weight is everything in aviation. Every pound saved means less fuel and more payload. Magnesium alloys are 40% lighter than aluminum ones with comparable strength. A modern passenger airliner contains several tons of magnesium alloys. Spacecraft and satellites too. When you need to put cargo into orbit, where every pound costs thousands of dollars, magnesium is irreplaceable. The automotive industry has fallen in love with magnesium too. Engine blocks, transmission components, wheel rims, all made from magnesium alloys, especially in sports and racing cars where weight is critical for speed and handling. A single magnesium rim weighs half as much as a steel one with the same strength. Electronics, another massive area where it shines. Laptop cases, tablets, smartphones, cameras, often made from magnesium alloys. Why? Lightweight plus excellent heat dissipation plus strength. Your smartphone or laptop might be packing magnesium right now. Magnesium is also used to protect other metals from corrosion, so-called sacrificial anodes. They're installed on ship hulls, underwater pipelines, oil rigs. Magnesium oxidizes first, protecting the main steel structure. Global magnesium production sits at around 1.2 million tons per year. China cranks out about 85% of all magnesium. Russia, the US, and Israel, other major producers. Magnesium prices swing from $2,000 to $4,000 per ton, depending on purity and market conditions. That's cheaper than aluminum, but pricier than steel. And so, traveling from bitter water in an English well, through dolomite quarries and endless oceans, through the hellish heat of furnaces at 1200 degrees, and the cold of crystallization, magnesium emerges into the world. A metal lighter than plastic and stronger than many steels. This is the story of how humanity learned to transform rock and seawater into a material that lifts planes into the sky and sends satellites to the stars. Every time you board an aircraft, hold your smartphone or watch fireworks burning with blinding white flame. Remember, behind it all is magnesium, an ancient element we learned to tame just 200 years ago. A metal that taught us lightness and strength can go hand in hand. The metal of the future harvested from an infinite ocean that will serve humanity for thousands of years to come.
Imagine a gas capable of changing the course of history. It can disinfect water, create plastic without which modern life is unthinkable, and at the same time become a deadly weapon. This is chlorine. Annually in the United States, over 12 million tons are produced, as much as 120 Gerald Ford aircraft carriers weigh. But the real mystery isn't in the numbers. It's hidden in the technology itself. How does simple salt water, with the help of electricity, give birth to 3 products that support entire industries? Watch carefully. At the end of this video, you'll learn a fact that will forever change your understanding of this invisible foundation of modern civilization. The United States is one of the world's largest producers of chlorine. Annually, factories in the country produce over 12 million tons of this gas. This figure simply doesn't fit in one's head. Imagine the weight of the Gerald Ford aircraft carrier, the world's heaviest military vessel. That's about 100,000 tons. This means that in 1 year, American industry produces as much chlorine as 120 such carriers weigh. Everything begins not in a laboratory, but deep underground. The main ingredient for our recipe is ordinary rock salt, or sodium chloride. It's either mined in mines or, much more efficiently, pumped from underground. Water is pumped into deep underground salt deposits. The water dissolves the salt, forming a saturated saline solution called brine. And it's precisely this concentrated salty solution that's our raw material. But it's still dirty. It's full of impurities, calcium, magnesium, and other minerals. Therefore, before the main show begins, the brine undergoes thorough purification. It's passed through an entire series of tanks where, with the help of chemicals, all impurities are precipitated and filtered from it. At the output, we obtain a perfectly clean, transparent, and very salty solution, ready for the main event, electrolysis. These are electrolyzers, or cells. It's precisely here that all the magic will occur, or more accurately, all the chemistry. Let's imagine one such electrolyzer. Essentially, it's a box into which our pure saline solution is poured. And into this solution are immersed two electrodes, a positively charged anode and a negatively charged cathode. Now to these electrodes is applied a direct electrical current of colossal force. And here the breakdown begins. The salt molecule in water breaks down into positively charged sodium ions and negatively charged chlorine ions, and the electrical field forces them to move. The positive sodium ions, like a magnet, are attracted to the negative cathode, and the negative chlorine ions to the positive anode. Two such chlorine atoms, having lost their charge, immediately unite, forming a molecule of gaseous chlorine. Billions of these molecules gather together and on the anode surface begin to appear tiny bubbles of greenish-yellow gas. This is our chlorine. The main resource for chlorine production is electrical energy. The chlor-alkali industry is one of the largest consumers of electrical energy in the United States. To produce 1 ton of chlorine requires approximately 2,500 kilowatt-hours of electricity. Now, let's multiply this by 12 million tons per year. It turns out that this industry annually consumes about 30 billion kilowatt-hours. That's more than the annual electricity consumption of entire states such as Vermont or Wyoming. But they don't transform into metallic sodium. Instead, electrical current splits the water molecules present in the solution into hydrogen and hydroxide ions. At the cathode are released bubbles of pure hydrogen. This is our first byproduct. And the hydroxide ions remaining in the solution combine with our sodium ions, forming sodium hydroxide, or caustic soda. This is our second incredibly valuable byproduct. But here arises an enormous problem. We've just obtained 3 substances, chlorine, hydrogen, and caustic soda, and they must not be mixed under any circumstances. Chlorine and hydrogen together form an explosive mixture, and chlorine and caustic soda react, forming bleach, which we don't need at all. This membrane, made from special polymer, resembles a bouncer at a nightclub. It allows positive sodium ions through, permitting them to pass to the cathode, but blocks negative chlorine ions, preventing them from entering the cathode space. Thus, chlorine is born and collects in one part of the cell, whilst hydrogen and caustic soda collect in another. Now we need to gather our harvest. From the anode chamber is continuously pumped wet, hot, greenish-yellow gas. First it must be cooled, then it must be dried. Chlorine is incredibly aggressive, especially in a wet state. It corrodes almost everything. But there's one substance it doesn't touch: concentrated sulfuric acid. It's compressed under enormous pressure and simultaneously cooled. Under this double assault, the gas transforms into a transparent, amber-yellow liquid resembling oil. This liquid chlorine is far more convenient to transport and store. It's poured into special thick-walled steel tanks or railway wagons. Every step of this process occurs under conditions of absolute seal because leakage of this gas is deadly dangerous. And what about our byproducts? They're no less important. The hydrogen we obtained is collected, purified, and used either as fuel for the factory itself or sold. And the caustic soda solution that formed is pumped out, concentrated, and sold. And so, from simple salt water, passing through it an enormous quantity of electricity, people have learned to obtain three extremely important substances at once, which are the foundation for thousands of other products. Now let's look at where all this enormous quantity of chlorine goes. You might think it all goes to disinfecting swimming pools, but that's merely a drop in the ocean. In reality, less than 5% of all chlorine is used for water disinfection. And where does the remaining 95% go? It's a key building block for other products. About 40% of all chlorine goes to producing this universal plastic. Vinyl windows in your house, water pipes, medical drips, the credit card in your wallet, all of this was born thanks to chlorine. Another 40% approximately is used for creating thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides, the list is endless. And chlorine is also a key component for bleaching paper, giving it that very clean white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we obtain approximately 1,100 kilograms of caustic soda. This means that annually, American industry produces over 13 million tons of this important alkali. This makes chlor-alkali production a perfectly balanced business. And now imagine what holds enormous suspension bridges in the air, which daily withstand the weight of thousands of cars and hurricane-force wind gusts. Not concrete and not steel in the columns, but an invisible hero, steel cable. From thin, almost fragile wires, they create structures capable of bearing hundreds of tons. The secret lies in technology that transforms a simple metal rod into a sinew that never gives in. American factories have already woven over 800,000 kilometers of cables, and each meter is like a separate artery of civilization. But there's a detail that's not written about in textbooks, and you'll discover it only at the end of this video. Everything begins with selecting raw materials, high-quality steel wire that must possess exceptional strength and flexibility. These wires pass through a cold drawing process where thick steel rods are pulled through special holes, gradually reducing their diameter to thin but extraordinarily strong threads. This process doesn't simply make the wire thinner, it enhances its mechanical properties, making it resistant to breaking. Imagine that each meter of this wire can withstand enormous loads whilst remaining flexible and elastic. After the wire is ready, the most interesting part begins. Forming the steel cable. Dozens and sometimes hundreds of such threads are twisted into strands, then woven into complex structures. Each wire layer has its purpose. Internal threads bear the main load, whilst external ones protect against wear and corrosion. The entire process resembles creating living tissue, where each thread is a separate vein that together forms a strong and reliable whole. Particularly impressive is the precision and control with which these cables are manufactured. Each stage is accompanied by strict testing. They check tensile strength, resistance to bending, and impact of weather conditions. Testing is conducted using special equipment that simulates the loads the cable will experience during bridge operation. This is extremely important, as bridges often stand in human environments or in locations with aggressive climates. Thanks to these coatings, cables not only maintain their strength, but also extend the bridge's service life, ensuring safety and reliability. Imagine the production scale. Factories that can manufacture thousands of tons of steel cables annually, unwinding and weaving hundreds of kilometers of wire. American manufacturers, for example, have many years' experience and employ the most modern technologies, allowing them to create cables for the world's most famous bridges. It's known that American Bridge Company has laid over 800,000 kilometers of steel cables for suspension bridges. Another aspect that impressed me is the role of engineers and technologists who constantly improve production processes. They work to make cables even stronger, lighter, and more resistant to extreme loads. Using new alloys, improving twisting and coating methods, all this makes modern steel cables genuine masterpieces of engineering thought. During the tour, I saw how enormous spools of steel wire move smoothly along conveyors, how wire passes through cold drawing, and how craftsmen control every centimeter of this process. American manufacturers, such as American Bridge Company, have enormous experience in manufacturing steel cables for the country's largest and most famous bridges. They produce thousands of tons of cables annually using modern technologies and strict quality control. It's known that for suspension bridges, they use cables with multi-layered structure that can withstand loads of hundreds of tons per square centimeter. During Brooklyn Bridge construction, for example, each of the main cables consisted of 19 separate strands, and each strand of 278 wires. This provided an enormous strength reserve. Steel cable production in the U.S. is a combination of tradition and innovation, where the craftsmanship of engineers and technologists is complemented by automated lines and modern equipment. Each stage, from raw material selection to protective coating application, is controlled with maximum attention, as thousands of people's safety who daily use bridges depends on this. European enterprises, particularly in countries like Germany, France, Italy, as well as Ukraine, Romania, and Poland, play an important role in supplying steel cables for bridge construction of various scales. Modern bridges are the result of millennia of engineering thought development, where traditions, innovations, and the most modern materials combine. They not only perform the function of connecting shores, but also become city symbols, cultural monuments, and technical masterpieces. Modern engineering marvels include the Falkirk Wheel in Scotland, a unique rotating boat lift that connects two canals and allows lifting boats through 180 degrees. This structure is not only functional, but also impresses with its futuristic design. Cable-stayed bridges, such as the Golden Gate in San Francisco, demonstrate the application of steel cables that withstand enormous loads and ensure structure longevity.
This ship doesn't go around the ice, it goes straight through it. 10 feet of frozen ocean, and it doesn't care. I'm standing in a shipyard where they're assembling the hull of a nuclear-powered icebreaker, and in front of me is a giant steel skeleton that will soon be working where temperatures drop below -50, and ice pressure can crush any ordinary structure like a tin can. You know, I usually go look at things you can touch without risking your cheek freezing to them. But today, I slightly overestimated my ambitions. And right now, I'm going to show you how a machine is born that makes even the Arctic itself back down. The first thing that hits you at the shipyard isn't the size, though the future vessel stretches over 500 feet long, and individual hull plates run several inches thick. What stuns you is the steel itself. They don't use ordinary rolled stock here. An icebreaker hull demands special steel grades that stay flexible even in brutal cold. Regular steel turns brittle in the freeze. Strike it, and it'll crack like glass. This stuff, though, has to take impacts from ice fields and not fail. The engineers explain it simply. The hull needs to give a little, flex slightly under pressure. Otherwise, the Arctic will just snap it. Massive steel plates arrive at the yard already rough processed from the rolling mill. Each plate weighs dozens of tons, and when the crane lifts one into the air, it looks like a chunk of an apartment building somebody randomly decided to relocate. But the icebreaker's shape doesn't appear all at once. First, these plates pass through giant rollers that slowly, with enormous force, bend them to the required angle, giving the metal that crucial curve without which the hull can't push ice aside. In front of me, steel rollers, each as thick as a decent tree trunk, stacked one above the other. Between them, they slowly feed a flat steel sheet. Heavy, rigid, seemingly completely inflexible at first glance. The operator gives the command, and the mechanism starts moving. The rollers rotate at low speed, but with massive force. The sheet gradually gets pulled inside, and at some point, you can see it start to change shape. First, it's a barely noticeable bend. Then the radius increases, and the metal's no longer flat. It curves smoothly, as if obeying someone's will. The sound here is unique, a muffled pressure, grinding, and a slight crackling, like the metal reluctantly gives in. I'm standing nearby, and I hear how the steel literally groans under the load, a sound like you're pressing on something really stubborn, and it's grudgingly surrendering. They might roll the sheet several times, adjusting the roller positions each time, until they get the exact angle or curvature. And there in front of you is no longer just a piece of steel, but part of a future hull that perfectly matches its contours. By the way, if you're into stories about how seriously complex and powerful machines are built, hit subscribe so you don't miss the next episode. Now, let's keep going. Next comes the assembly of sections, and this looks like a giant construction set, except each block weighs as much as a small locomotive. Individual hull blocks are assembled in the shop. These can be sections 60 or even 100 feet long. Inside each block, there are already bulkheads, cable routes, and even foundations for future decks. In other words, the hull isn't built from scratch in one spot. It's assembled in pieces, like a puzzle, just really heavy and really hot to produce. I walk into the shop and there are finished sections already standing there. These aren't just sheets of metal, they're entire fragments of the future ship. Inside each one, you can see passageways, openings for cables, spots where pipes, wires, and entire life support systems will run later. Then these blocks are transported to the slipway and joined together. The cranes move in. They lift the section into the air slowly, smoothly, no sudden movements, and transport it to the slipway. There, they carefully lower it and fit it against the already installed parts of the hull. At this moment, you literally see separate pieces starting to come together as one. The future icebreaker takes shape right before your eyes. Welding is a whole different story. You can't just run a bead and go grab coffee. Every joint goes through multiple levels of inspection. First, the welder lays the main seam. Then they check it with ultrasound to make sure there are no voids or cracks inside. If something's off, they cut it out and do it over. I watched them redo one seam 3 times, and nobody even got stressed. That's standard practice here, because the price of a mistake in the Arctic isn't just a breakdown, it's a potential catastrophe. And that's how it goes. Every seam, every joint, along the entire length of the hull. We should talk about the hull shape. An icebreaker doesn't just have a strong bow, it's specifically designed to climb up onto the ice and break it with its own weight. That's why the bow section has that distinctive slope, and they reinforce it with extra layers of steel. In some spots, the thickness multiplies several times over, and inside they add ribs that distribute the load along the entire length of the ship. While I'm walking around here, there's constant movement everywhere. Cranes, platforms, people in hard hats, for whom all this is just another workday. Though honestly, when they're moving a hull section weighing dozens of tons right over your head, you kind of rethink the word ordinary. One of the engineers jokes that the scariest thing here isn't the cold or the metal, it's when someone forgets their lunch in the shop, because finding it among all this scale is practically impossible. When all the sections are connected, the hull starts taking its final shape. Its length becomes physically tangible. You walk alongside and catch yourself thinking it's like strolling past an apartment building, only horizontal. The height of the hull is impressive too. Several levels that will eventually become decks, engine rooms, and crew quarters. After that comes surface treatment. The metal gets cleaned, anti-corrosion coatings applied, painted with special compounds that reduce water friction and protect the hull from salt and ice. It looks like cosmetics for a giant, but in reality, this coating determines how many years the ship can operate without major repairs. And that's not an exaggeration. Arctic saltwater and constant ice friction can destroy unprotected metal in just a few seasons. Modern nuclear icebreakers can ram through ice up to 9 feet thick while underway, and the newest designs are rated for ice up to nearly 15 feet thick. Power, that's a whole other story. Heavy icebreakers can pump out over 75,000 horsepower, and without that, they simply wouldn't budge the ice. I'm standing here staring at this hull, and it hits me. This isn't a finished vessel yet. There's no reactor in here, no propellers, no control systems. But even now, the main thing is crystal clear. This is a structure built to battle the elements, where every millimeter of steel serves a purpose. And when she heads out to sea, she won't just sail. She'll carve a path where other ships wouldn't even dare to go. I'm gonna stick around here a bit longer. Listen to that metal grinding. Watch these machines come to life. Then head out to prep your next adventure. Because after something like this, you want to find something just as massive, just as complex, just as beautifully insane. When you stand next to a structure like this, you start seeing what humans can actually build differently. Not on a computer, not in theory, but right here, with hands, steel, and fire. And I think I've already got a couple ideas where to head next. So stick around, it's gonna be good.
Every second, the world transmits over 3 billion gigabytes of data. But do you know that all of this is thanks to a thread thinner than a human hair? And that this thread begins with ordinary sand? Not beach sand, but perfectly pure quartz, where there's only 1 impurity particle per million particles. To create fiber optic cable that carries light at speeds exceeding 300,000 kilometers per second, you need to journey through chemical vapors, sterile laboratories, a furnace at 2,500 degrees, and lasers that monitor every microcrack. This process looks more like manufacturing a spacecraft than a cable. But it's precisely this that forms the foundation of the internet you're using right now. To create a thread capable of transmitting light at speeds approaching 300,000 kilometers per second, you must begin with sand. But not just any sand, only special, exceptionally pure quartz sand, where the primary substance is silicon dioxide. For fiber optic production, sand with a silica content exceeding 99.9% is used, which means that in 1 million particles, only 1 particle is an impurity. Just imagine, in every kilogram of raw material, no more than a few milligrams of impurities. And this is critically important, because even a tiny particle of foreign metal can cause light scattering or absorption. And then a signal that should have traveled nearly 100 kilometers without amplification simply vanishes. Raw material for fiber optics isn't simply washed or filtered, it's purified at the molecular level. Manufacturers often employ gas chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and precipitated as the purest vapor. And only then is it converted back into glass. Add to this strict temperature control, humidity, and airflow in clean rooms, and you'll get an idea of how far removed this is from an ordinary sandy beach. Production laboratories resemble NASA's sterile zones more than a glass workshop. And all of this to ensure that every meter of future fiber contains not a single defect. A large transparent glass cylinder, which will later be melted and drawn into an extremely thin thread, is the fiber optic preform. This enormous glass blank is made using a method called vapor deposition. In a large furnace, air is mixed with extremely pure gases. These vapors reach the inner surface of a transparent tube that's heated intensely. When the vapors touch the hot wall, they settle and transform into tiny glass droplets, like dew collecting on a leaf in the morning. Gradually, these droplets accumulate layer by layer until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it closes into a dense solid rod. This is our preform. The preform is placed in a special furnace where the temperature reaches approximately 2,600 degrees Celsius. This temperature is so high that the glass becomes soft and begins to melt, like caramel on a hob. When the preform's end melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and from it forms the finest thread. This thread, the optical fiber, is drawn at speeds of roughly 300 meters per minute. Imagine, that's faster than a cyclist moving through the city. It's important that the thread has the same thickness along its entire length. Optical fiber thickness is typically around 125 microns. This is very, very thin. For comparison, the average human hair has a thickness of around 100 microns. To keep this diameter under control, special instruments are positioned in the process. They monitor the thread in real time and measure its thickness. If the thread begins to become thicker or thinner, the system automatically changes the drawing speed or furnace temperature to correct it. After the optical fiber has been drawn and has become a thin, transparent thread, it needs protection. The fiber is extremely thin and fragile. Therefore, immediately after drawing, it's coated with a special protective layer. The thin thread is drawn from the furnace. After the furnace, it immediately enters a coating machine, a special device that dresses the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. This resembles a small tube or nozzle, inside which sits molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly poured onto it. This coating layer typically consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks. The secondary coating is harder and stronger, protecting from external influences, dust, and scratches. After applying the liquid coating, the fiber passes through special forming rollers. They regulate the layer's thickness and evenness. After the polymer has been applied and formed, the fiber passes through an ultraviolet light zone. Here, under UV lamp influence, the polymer instantly hardens. This process is called polymerization. Those of you who get manicures know how this works. Ultraviolet lamps activate chemical reactions in the polymer. Thanks to this, the coating quickly becomes hard whilst maintaining its elasticity. This is an extremely rapid process. The coating hardens literally in fractions of a second. This method doesn't heat the fiber so it doesn't damage it. The entire machine is equipped with sensors and control systems. They constantly measure coating thickness and fiber feed speed. At the end of all this technological wizardry sits a spool module, rotating with a hum resembling a jet engine sound in miniature. The fiber, resembling transparent silk, lays evenly and precisely coil against coil. The spool moves smoothly left and right with millimeter precision. Around it are sensors, lasers, cameras. They vigilantly monitor that the fiber lays evenly and doesn't twist. With every minute, more and more layers appear on the spool. Imagine, in just a few hours, there are already several kilometers of the finest, almost invisible fiber. And all of this without a single break, without a single scratch. Before assembly into cable begins, fiber from the spool is carefully rewound onto the production line. Since one cable typically contains several fibers, individual threads are combined into ribbons or modules. These ribbons or bundles are then placed into buffer tubes. These are thin, flexible plastic channels that provide the fiber space for micro movements. This is important because when temperature changes or the cable bends, the fiber slightly expands or contracts. Inside these tubes, gel may also be added that repels water and absorbs vibrations. Around the buffer tubes, reinforcing elements are added. Fiberglass or Kevlar. These are extremely strong threads that protect the cable from stretching. Metal wire is needed for additional mechanical strength. The central rod is a rigid element at the center that maintains the cable's shape. All of this is wrapped with an outer sheath. This is a dense plastic or polyethylene tube resistant to ultraviolet light, moisture, rodents, and temperature fluctuations. The cable is tested. Each fiber's transmission capacity is checked, along with bending strength and moisture resistance. Then it's wound onto large drums, marked, technical documents are added, and it's ready for transport and installation. From stone to wool. Sounds like science fiction, right?
But here's the reality. The world cranks out over 8 billion square meters of mineral wool every single year. That's enough to insulate and soundproof millions of buildings. Ever wonder how chunks of rock, basically useless on their own, transform into one of the most effective insulation materials out there? Today, we're going inside the world's largest mineral wool factory to unlock the secrets behind this cutting-edge manufacturing process. About 1,000 years ago on the Hawaiian Islands, in the heart of the Pacific Ocean, something amazing happened. Streams of molten lava, stretched by the wind, formed thin fibers that wove together into a natural insulating blanket. According to legend, these were the hairs of the goddess Pele, torn from her head each time a volcano erupted. In the early 20th century, a group of scientists also discovered the extraordinary insulating properties of this volcanic material. And from this knowledge, rock wool was born. But to insulate millions of homes, Hawaii's lava alone wasn't enough. Humanity had to recreate the forces of nature through industrial processes. In the United States, states with large basalt deposits like North Carolina, Missouri, and Utah became the primary sources of raw material for large-scale rock wool production. To produce stone wool, the first thing you need is raw material, rock. The most common types are basalt and dolomite, hard minerals that can withstand high temperatures. At the Cardinal Aggregates open pit quarry in Ohio, USA, over 700,000 tons of stone are extracted annually. The first step is removing overburden with giant excavators. For every 10 feet of removed earth, about 1,600 tons of basaltic rock are uncovered. Next comes drilling and blasting. Powerful drill rigs cut through stone at nearly 5 feet per minute, creating a grid of boreholes. Then, 15 to 30 holes are carefully loaded with explosives. Under the supervision of blast engineers, each explosion releases 15 to 25,000 tons of raw stone. After crushing, the stone is delivered to the crushing plant, where massive blocks are ground down to pieces smaller than 10 inches. Each bucket is weighed electronically before being dumped into waiting trucks. On peak days, over 400 trucks leave the quarry, delivering 16 to 18,000 tons of stone daily to production facilities. From these very blocks, in the next stage of melting and spinning, the stone is transformed into millions of thin mineral fibers, the foundation of modern stone wool insulation for buildings. Heavy trucks loaded with basalt from the quarry roll into the plant's receiving zone, marking the beginning of a massive industrial journey. Uniform-sized stones head straight to the production line, while rough chunks and impurities continue along conveyors toward the crushers. Onto the dosing conveyor, alongside the basalt stones, glossy black coke particles are evenly distributed. Adding coke doesn't just provide intense heat for the furnace, it also regulates the chemical composition, helping the basalt melt faster and more uniformly. Next comes the melting stage.
The basalt and coke mixture gets fed into a massive furnace where temperatures climb above 2,700 degrees Fahrenheit. Under this intense heat, everything dissolves into a glowing red stream of lava rich in silica, aluminum oxide, calcium oxide, and magnesium oxide, transforming into a thick liquid almost identical to volcanic magma. When the molten stream pours out, sparks fly in every direction, and workers in ceramic fiber suits and metal masks step forward to check working conditions. These furnaces run non-stop, 24/7, because shutting them down not only burns through massive amounts of energy to restart, but also shortens the lifespan of the refractory lining. From the furnace, a stream of glowing lava flows onto high-speed spinning wheels. When the molten material hits the rotating surface, it flies outward and stretches into fibers thinner than a human hair. At the same time, a stream of hot air follows the rotation, carrying the fibers outward and rapidly cooling them in the air, locking in their thin yet strong form. The result is a rain of mineral fibers that settles into a light, fluffy mat with remarkable heat resistance and sound-absorbing capabilities. Rock wool fibers are collected immediately after formation, carried by a stream of hot air, and laid down evenly on large rotating drums or wide conveyors. Layer by layer, the thin strands form a continuous blanket of mineral wool. Powerful fans and suction channels are precisely calibrated to distribute the fibers uniformly. At this stage, the material is still soft and fluffy, like a flowing sea of white fibers. The rock wool takes the shape of a block, but the initial fiber streams are only a few inches thick, so they need to be layered continuously. The rock wool stream moves forward to the layering stage, where fiber mats are stacked one on top of another to increase thickness. This process typically increases the depth of the sheet from a few inches to 8 to 12 inches, depending on its end use. After layering to the desired thickness, the mineral wool mat feeds into a massive system of roller presses. Here, even pressure is applied across the entire surface, compressing the loose fibers into a sheet with precise dimensions. At the same time, mechanical arms along the sides of the conveyor repeatedly press the edges, holding them tight and preventing the material from spreading outward. The result is a densely compressed block of mineral wool with a uniform thickness of 8 to 12 inches. Once the mineral wool block is tightly compressed and stabilized, it passes through a high-speed cutting system. Blades trim away the excess edges, creating straight, even sides that match the desired shape. Then, additional cutters slice the thick blanket into individual panels or blocks, each with identical dimensions. By the end of this stage, the mineral wool transforms from a loose mat into neatly formed insulation boards. Each block is cut into standard panels, typically measuring about 2 feet by 4 feet, with thickness ranging from a couple of inches for residential applications to nearly 12 inches for heavy industrial insulation. The stone wool boards are ready now, but they've got to pass one crucial stage: quality control. Part of this process involves checking their hardness,
where pressure tests are applied to make sure the boards can withstand mechanical loads without losing their shape or density. And since mineral wool is both fireproof and insulating, a fire resistance test is mandatory. Here, they use a flamethrower that scorches the surface to temperatures of around 2200 degrees, while a person can sit right behind it reading a newspaper, feeling nothing. After inspection is complete, the stone wool insulation boards are carefully wrapped in heavy-duty plastic film, then loaded onto trucks and shipped out to construction sites.
Every year, the world produces over 500 million tons of glass. Without it, there'd be no windows, smartphones, cars, or skyscrapers. But few people know that the journey to this perfect transparency doesn't start with glass at all. It starts with hot sand, heated in furnaces to temperatures exceeding 1600 degrees Celsius. This isn't just manufacturing, it's modern-day alchemy. Millions of tons of sand transformed into an ocean of molten glass, floating on liquid tin to create a perfectly smooth surface. You're about to discover the secrets of this process right here. Before hot sand becomes a transparent window, it all begins in a quarry. The primary raw material for float glass is high-quality silica sand. It must be almost perfectly pure, with a silicon dioxide content exceeding 99.5%. This sand is extracted from special deposits, typically deep underground. One of the most prized is Ottawa sand from Illinois. Pale white, fine as flour, and exceptionally pure. Quarries operate like giant anthills. Excavators tear through layers of earth, whilst lorries, 40-tonners, haul the sand to crushing plants. Then comes dry screening. The sand is cleaned of stones and the slightest impurities. Besides sand, glass contains several other components. Soda ash lowers the melting temperature. It's transported from salt deposits, particularly from Wyoming, in 23-kilogram bags or in bulk. Limestone stabilizes the structure. It's supplied from quarries and ground to a dust with particles under 1 millimeter in diameter. The mix also includes dolomite, aluminum oxide, saltpeter, and glass waste, what's called cullet. Cullet reduces the energy consumption for melting by up to 25%. After initial cleaning, all components are mixed in precise proportions, which are kept as trade secrets. A giant mixer the size of a 2-story house prepares the glass flour mixture. The finished mixture is transported to production by lorry and sometimes by rail or even on barges. Storage temperature must be controlled, no moisture whatsoever. The warehouse resembles a sterile grain elevator with silos, each with a capacity of roughly 560 cubic meters. The mixture is then automatically fed into the glass furnace, where within just minutes, everything that was sand and dust yesterday transforms into a boiling ocean of glass. The mixture enters the heart of production, the glass furnace. It's a genuine industrial volcano, over 60 meters long, with temperatures reaching 1600 degrees Celsius at the melting core. Raw materials are fed in automatically, several tons per hour. In the first 9 to 12 meters of the furnace, melting occurs. Components melt and merge into a glowing, viscous mass. Next comes the homogenization zone. The mass is stirred and matures until all bubbles and lumps disappear. And only then does it gently flow onto metal. This is where the magic begins. In the second stage, the mass enters a bath of molten tin heated to 1100 degrees. The glass literally floats on the metal, spreading into an even ribbon. Thanks to surface tension and the perfect flatness of the tin, a mirror-smooth surface forms on both sides, without polishing, without presses. thickness is controlled by stretching, special rollers, or electromagnetic fields either stretch or compress the glass ribbon. This way, the output can be glass ranging from 1.5 to 19 millimeters thick. The tin bath spans over 45 meters, and the glass slowly floats along it at speeds up to 7.5 meters per minute, cooling en route to 540 degrees Celsius. This is an absolutely critical moment, but even at this stage, it's not ready yet. Next comes the annealing zone. The glass ribbon passes through a long tunnel where it cools by several degrees per minute to relieve all internal stresses. Without this, the glass could later crack on its own. Its surface is like ice, smooth without a single scratch. The sheet size is impressive, up to 3 meters wide and over 9 meters long. In this state, the glass enters the cutting zone. Before it's cut, a computer scanning system analyzes the entire surface, searching for micro cracks, inclusions, stress points. Any find means that sheet's rejected. Cutting isn't mechanical anymore. Now it's laser or roller scoring. A microblade, similar to diamond, scores a line, and then gentle pressure snaps the glass precisely along that path. Sometimes sheets are cut straight to order, say 60 by 90 centimeters for construction glass or screen size for Tesla. Others go in standard formats to warehouses, where they're stored vertically on racks with rubber spacers. After cutting comes the calibration stage. Sheets are checked for thickness, geometry, straight edges. High-definition cameras scan every centimeter. Lasers analyze the corners. There are almost no human hands here, only at the final stage when workers in gloves mark the perfect sheets. In a world where glass has perfect transparency, marking is its name, passport, and craftsman's signature all in one. It's in the marking zone that each piece of glass is given its identity, where, when, by whom, and for what purpose it was created. The most common method is laser engraving. A special laser burns microscopic dots onto the surface, creating an indelible frosted inscription. Font thickness is less than 2.5 millimeters. This inscription can't be removed without damaging the glass, which is precisely why it's often used as an anti-tamper code. Sandblasting is used for decorative or premium glass. Through a stencil, abrasive is applied to the glass under pressure, forming a raised frosted mark. Then there's marking with ceramic inks. This method is used at the stage before tempering. Special paint is applied by printing, then baked at temperatures exceeding 1100 degrees. This marking is colored, noticeable, and extremely durable. It won't wash off, won't wear away, and won't fade. Marking can be either technical or branded. For instance, windows in luxury homes often proudly display the manufacturer's logo. In some projects, marking is even used for authenticity verification. For example, glass for armored vehicles or government buildings receives a serial number and QR code. The final stage is documentation. Every sheet gets a record in the system, like in a hospital. What sort of patient it is, when it was born, what properties it has, and where it's heading. This matters because glass isn't always dispatched immediately. Some batches are stored for months until their time comes.
Your smartphone would weigh over 2 pounds and be an inch thick. A can of Coke would cost $5. A Boeing 747 couldn't cross the Atlantic. It'd run out of fuel halfway. And half the stuff in your house simply wouldn't exist. All because of one metal that humans didn't discover until 1828 and couldn't mass produce until 1886. Before that, the world ran on iron, steel, copper, and bronze. Metals too heavy, too expensive, or too weak for modern life. Today, we're heading inside an aluminum plant, and I'll show you what properties emerge at each stage. This aluminum plant sits right on the riverbank. That's no accident. It's been running non-stop for over 120 years. It's here because it has direct access to massive hydroelectric power. That's critical because making aluminum takes more electricity than almost any other industrial process on Earth. Walk onto the grounds and the first thing you feel, a low hum from the transformers. The smell of superheated metal hangs in the air constantly. The plant never stops, not for a minute. The raw material is bauxite, a reddish-brown powder that arrives on ships from tropical countries, Jamaica, Australia, Guinea. If aluminum had never been discovered, we'd still be mining iron ore for everything. Steel production needs coal. It gives off massive emissions. Aluminum here, it runs on clean hydropower. Without aluminum, global carbon emissions would be roughly 15% higher from metal production alone. The first stage is processing bauxite through the Bayer process. The ore is crushed and mixed with caustic soda, then heated to 347 degrees Fahrenheit under pressure in autoclaves. Under these conditions, aluminum oxide dissolves while iron and silicon remain as red mud, a thick, bright, rust-colored mass that's diverted to special storage facilities. The output? Pure white aluminum oxide powder, also known as alumina. To produce 1 ton of alumina, you need to process about 2 tons of bauxite. This is where aluminum's first critical property is established: incredible corrosion resistance. In air, aluminum instantly forms an ultra-thin oxide film that locks the metal into protection against further oxidation. If we use steel, every outdoor structure would need constant repainting. Steel ships require dry dock and repainting every few years. Aluminum boats serve for decades without maintenance. Without this property, coastal cities would burn billions on infrastructure upkeep. The alumina is moved to the electrolysis hall, and this place is impressive. A massive room with rows of reduction cells radiating waves of heat. These are glowing rectangular pools about 15 feet long, filled with molten cryolite at a temperature of around 1700 degrees Fahrenheit. The surface of the cells flickers orange, and the air shimmers from the heat. The alumina dissolves in this bath. Then, a current of 150,000 amps is run through each cell, enough electricity to power 15,000 homes. The current rips aluminum atoms away from oxygen atoms. Pure molten aluminum sinks to the bottom. Oxygen rises to the top. This is the Hall-Héroult process, invented in 1886, and it's still the only economically viable way to produce aluminum. Before it, aluminum cost more than gold. Napoleon III used aluminum plates for his most important guests, while everyone else ate from gold ones. Without the Hall-Héroult process, aluminum would cost hundreds of dollars per pound today, and a can of soda would set you back a fortune. After a full day of operation, the molten aluminum gets pumped out and poured into crucibles, 10 tons each. The liquid metal glows with a soft, silvery light, nothing like orange cast iron or golden bronze. This shimmering metal demonstrates aluminum's most critical property, strength-to-weight ratio. Aluminum's 3 times lighter than steel, but with the right alloying, nearly as strong. A Boeing 747 made of steel would weigh 1,200 tons instead of 400. You'd need engines 3 times more powerful, burning 3 times more fuel. But carrying that extra fuel adds weight, which demands even more fuel. The tyranny of the rocket equation makes long-haul flights impossible. Without aluminum, commercial aviation as we know it doesn't exist. Short flights on steel planes? Possible. But New York to London would need 2 refueling stops, turning 8 hours into 20, while ticket prices would shoot up to several $1,000s. Molten aluminum gets poured into molds, forming ingots weighing several tons. Then they're reheated to 850 degrees Fahrenheit and pass through massive rolling mills. The rollers press down with thousands of tons of force, and with each pass, the ingot gets thinner and longer, transforming into sheets ranging from 0.02 of an inch to several inches thick. Rolling aligns the grain structure, locking in specific mechanical properties. Here's where another critical quality emerges: electrical conductivity. Aluminum conducts electricity 60% as well as copper, but weighs only 30% as much. Every high-voltage power line uses aluminum around a steel core. The aluminum conducts the current while the steel carries the load. If we had to use copper instead, the wires would be 3 times heavier, the support towers would need to be 3 times stronger, and spaced closer together. Building power grids would cost 4 times more. Rural electrification would never have happened, and your monthly electric bill would triple. Every sheet undergoes the strictest quality control, and there's a concrete reason for that. On April 28, 1988, Aloha Airlines Flight 243 was cruising at about 24,000 feet above Hawaii when passengers heard explosive decompression. The entire upper section of the forward fuselage tore away, exposing nearly 18 feet of skin and opening the cabin to the sky. One flight attendant was killed, 65 passengers injured. The investigation revealed that the aluminum fuselage had developed microscopic fatigue cracks after years of pressurization cycles. With every takeoff, the fuselage expands under pressure. With every landing, it contracts. Thousands of these cycles, and invisible defects appear in the metal. Tiny cracks grew and connected until the structure failed catastrophically. The aircraft had completed 89,000 flight cycles, and technicians couldn't detect such small defects. This tragedy completely transformed how the aerospace industry inspects aluminum. Today, every single sheet goes through eddy current testing, which detects surface cracks as small as 0.004 of an inch deep, ultrasonic testing that finds internal defects, and X-ray examination for critical components. Plus fatigue testing. Samples get bent millions of times, simulating decades of flight cycles to verify the alloy's reliability. The rejection rate for aerospace aluminum is 12%. Every 8th sheet fails inspection and gets sent back for remelting. That number seems high, but after the Aloha disaster, the industry decided, better to lose metal than lives. Aluminum that passes inspection goes to manufacturers, who turn it into everything, from aircraft to soda cans. A major plant produces around 300,000 tons annually. And virtually all that rejected metal doesn't go to waste. Aluminum can be remelted infinite times without losing its properties, and remelting takes just 5% of the energy needed for primary production. Without aluminum, cans would be made of tin-plated steel, weighing 3 times as much. A 12-pack of Coke, 24 pounds instead of 9. Shipping costs triple, prices double. Construction would look completely different. Modern curtain walls use aluminum frames, strong enough for glass but light enough that buildings don't need massive reinforcement. Without aluminum, tiny windows in thick walls, or steel frames so heavy that buildings over 50 stories become impractical. Modern glass skyscrapers don't exist. Computers and smartphones would be different too. That aluminum laptop body would have to be plastic or magnesium. Plastic isn't rigid enough and cracks. Magnesium is light but catches fire during machining. The plant's been running for over 120 years, producing roughly 20 million tons of aluminum, turned into planes, cars, buildings, power lines, packaging, and electronics. Without the electrolysis process running in those reduction cells, none of this exists. We'd be trapped in a world that's heavier, more expensive, and far more limited.
Every year, shipyards launch massive icebreakers and cruise liners, vessels weighing tens of thousands of tons, capable of operating for months in the planet's harshest seas. But few realize their engines are no longer inside the hull. Engineers took a radical step. They moved a power plant generating over 22 megawatts. That's more than 30,000 horsepower. And dropped it directly beneath the ship's bottom in a sealed steel pod weighing 320 tons. That's the weight of 2 fully loaded Boeing 747s. Inside that pod, a rotor misalignment by a fraction of a millimeter can shred bearings and destroy the entire drive system in just days. Watch this video to the end, and you'll discover how this underwater power plant is built, what installation mistake gets permanently hidden beneath the waves, and why this invisible enemy can obliterate a ship weighing thousands of tons in a matter of days. At first glance, it looks like a massive metal tail bolted to the ship's bottom. But inside, a full-blown electric motor. They don't mount it in the engine room like they did for decades. Here, it's the opposite. They drop the motor straight into the water, seal it tight in a steel shell, and make it work right there in the ocean. For years, no repairs, under constant seawater pressure. That's exactly why this thing's treated almost like a submarine. The idea of moving the engine outside the hull showed up relatively recently, even though engineers had been thinking about it for decades. Back in the mid-20th century, shipbuilders were trying to ditch the long shafts, gearboxes, and complex mechanical drives that ate up massive space inside the ship and bled power at every connection. The real breakthrough came in the late 1980s when Finnish engineers working on icebreakers for northern seas proposed a radical solution: move the electric motor directly into the rotating pod under the hull. If engineering stories like this grab you the way they grab me, subscribe to the channel right now so you don't miss the next episode. Hit that bell and every new video will show up for you immediately. The work was carried out by specialists from a shipbuilding company looking for a way to make vessels more maneuverable in ice. The first experiments looked risky. The engine had to be completely isolated from seawater and made to run for years without any access to it. In 1990, the first working units appeared, and just a few years later, the technology began being installed on actual icebreakers. It turned out that this design didn't just work. It worked better than any traditional setup. When it became clear that the azimuth thruster allowed a ship to move in practically any direction without turning the hull, the system was quickly adopted by cruise liner builders. This thruster can rotate 360 degrees, making conventional stern rudders and separate bow thrusters simply unnecessary. Maneuverability increases so much that a huge liner can pull up to a dock nearly sideways without tugboat assistance. Since then, this design has gradually changed the very concept of where a ship's heart should be. Not inside it, but right beneath it. I walk past hull sections that were still separate steel plates just hours ago, each one several inches thick and weighing several tons. These are already curved metal sheets, pre-rolled, so the future capsule has a smooth, streamlined shape with no abrupt transitions. No right angles here, no unnecessary joints. The form is dictated by water, not manufacturing convenience. Overhead cranes slowly lift these elements and bring them together like assembling an underwater projectile. Between the parts, they leave a narrow gap where the weld seam will go. During welding, sparks fly everywhere, and the metal glows orange. Workers move slowly, passing over every inch of the joint multiple times. No rushing, no wasted motion. First comes the inner seam, then the outer. And after that, the surface gets carefully ground down so there's not a single protrusion left to create extra drag in the water. When the hull finally closes up, it already looks like a smooth steel torpedo. Tight, solid, without a single flaw on the outside. After that, the inspection begins. Welds are scanned with ultrasound and X-rays searching for even the tiniest pores inside the metal. Any suspicious section gets cut out and re-welded, no compromises. Then they seal the capsule and pressurize it far beyond what it'll face underwater in actual conditions. If there's a weak spot anywhere, it'll show up immediately. Only after passing all tests is the hull declared ready to withstand years of service in cold seawater and constant ice impacts. Once the steel capsule is fully welded and tested, the moment arrives in the shop that the entire hull was essentially built for. They need to install the electric motor, the main power source for the future vessel. And this is where you realize just how massive everything is in marine engineering. Before installation, the motor sits on a special platform looking more like part of a power plant than ship machinery. Its diameter, nearly 10 feet, and its weight is such that regular lifting equipment isn't even considered an option. Only heavy overhead cranes work here, with every movement pre-calculated and coordinated. The rotor, the spinning part of the engine, gets lifted separately. It's a massive metal ring with copper conductors that weighs more than a fully loaded semi-truck. The crane starts moving so slowly it's almost invisible to the eye. The operator works on commands from several engineers stationed around the housing, constantly monitoring the component's position. There's no room for sudden movement and no room for error. Even a shift of a fraction of a millimeter can mean misalignment that'll show up during operation as severe vibrations. And vibrations at this power level aren't just an inconvenience, they're a disaster. When the rotor hangs over the open capsule, the most nerve-wracking phase begins. They literally lower it millimeter by millimeter, constantly measuring clearances with laser instruments. Inside the housing, bearings and support elements are already installed, and everything has to align to within thousandths of a millimeter. If the engine shaft is even slightly off from the geometric center of the capsule, a spinning imbalance will develop that the entire ship will feel. At operating speed, this imbalance turns into a constant hammering that can destroy bearings or damage the housing from the inside in a matter of weeks. After the rotor is seated, engineers won't allow the crane to be removed for a long time. A series of checks begins. They measure alignment, manually rotate the shaft several times, listen carefully to the sound of metal. The slightest unusual noise and the part gets lifted back up. Sometimes they raise the motor again and adjust its position, spending hours for just a few millimeters of correction. Everyone here understands. Once the capsule is sealed, there will never be access inside again, so perfect precision matters more than any installation speed. When the motor finally settles into place, the entire structure suddenly looks complete. An empty steel shell transforms into a real propulsion system. This is the moment you can consider the birth of a system that will later spin the propeller, turn a multi-thousand-ton vessel, and operate for years underwater, where no human will ever see it again. Modern units can pump out up to 22 megawatts of power. That's the equivalent of more than 30,000 horsepower. To put that in perspective, a single engine like this could supply electricity to a small town of 25,000 people. And this is a mechanism that operates completely underwater, hidden from view, impossible to service in the open ocean. It's designed with reliability margins years into the future because scheduled maintenance is only possible in dry dock. A fully assembled unit with engine and propeller can weigh over 320 tons. The propeller that attaches to the pod often exceeds 23 feet in diameter. Each blade on a propeller like that weighs as much as an adult African elephant. Yet this entire system has to run absolutely smooth. Any vibration at these power levels instantly transfers to the hull and gets felt by passengers on every deck. Once the engine is safely tucked inside its steel housing, the final stage begins, installing the propeller. If the pod itself is the muscle, then the propeller is the hands that push against the water and drive the ship forward. Each blade is manufactured from a special alloy of bronze, aluminum, and nickel. This metal needs to be strong enough not to bend under the pressure of thousands of tons of water, yet smooth enough not to create unnecessary turbulence. The blades arrive at the pod on special pallets, each wrapped in protective film like a piece of jewelry. Installation is carried out using hydraulic rams. The propeller is mounted onto the engine shaft protruding from the pod, and here precision is once again measured in thousandths of a millimeter. Any misalignment will cause the propeller to vibrate at operating speed, and that vibration will destroy the engine bearings within days. When the propeller finally locks into place, it's secured with a massive nut, tightened with several thousand Newton-meters of torque. After that, a streamlined cap is installed on the hub to ensure the water flow past the propeller is perfectly smooth. The entire assembly is coated with special paint that marine organisms and barnacles won't stick to. Because even a few centimeters of buildup on the blades can reduce engine efficiency by 5 to 7%, translating to losses of hundreds of thousands of euros per year.
Every single day, the United States alone extracts over 9 million barrels of oil. A single barrel holds nearly 159 liters. Now multiply that by thousands of wells across the planet. But have you ever stopped to consider what oil actually is and how it is formed? This isn't just a black liquid. It is the result of immense geological forces acting over millions of years deep within the earth. Oil is born from the remains of ancient life, transformed by pressure and heat into a liquid hydrocarbon. And from there, the modern story begins. A high-stakes hunt, deep earth drilling, and the incredible process that turns this primordial substance into the fuel that moves our world. It's expected that the average daily oil output in the U.S. will soon reach 9.9 million barrels. But what exactly is this substance we call oil? The process of its formation is a slow, powerful saga that unfolds over geological time. It begins with the accumulation of organic material, the remains of ancient plants and animals at the bottom of seas and lakes. Over millions of years, these remains are buried under layers of sediment. Under the immense pressure and heat, this organic matter transforms into a waxy substance called kerogen. Further heating, in a temperature window between 60 and 150 degrees Celsius, triggers the thermal breakdown of kerogen, creating liquid hydrocarbons. And that is what oil is, the distilled essence of ancient life. Once formed, this oil migrates through porous rock until it reaches a geological trap, a structure that blocks its path. Here, it accumulates, forming a reservoir. To find these hidden reservoirs, we must first understand the earth beneath our feet. This is the world of geological surveying, one of the most complex and expensive stages of the process. Scientists use satellite imagery, magnetometers, and seismic waves. Seismic surveying is particularly spectacular. Controlled underground explosions are triggered to send shock waves deep into the earth. By reading the echoes, geologists can map the subterranean landscape and identify potential traps. When a promising zone is identified, the drilling begins. A land or offshore rig becomes a giant mechanical creature operating day and night without pause. The drill string, steel pipes with a cutting bit at the end, bites into the earth, rotating at up to 200 revolutions per minute. A special drilling fluid is pumped down to lubricate the bit and carry rock cuttings back to the surface. A modern well can reach depths of 3 to 5 kilometers, and in some cases 10 or even 12. In Texas or Saudi Arabia, wells are drilled over 8 kilometers long, often with a significant horizontal section to maximize contact with the reservoir. A single drilling operation can cost tens of millions of dollars with no guarantee of success. But when a well strikes oil, it begins its journey to the surface, either under its own pressure or with the help of powerful pumps. Saudi Arabia is one of the world's oil titans. In February, the kingdom was producing nearly 9 million barrels per day, and its position is only set to strengthen as Saudi Aramco has recently discovered 14 new oil and gas fields. Once the well is completed, the extraction phase begins. In a rich reservoir, the natural pressure is enough to force the oil to the surface. This is known as a gusher, and while it looks impressive, it's now considered an outdated and dangerous method. Modern wells are fitted with complex valve systems known as Christmas trees that allow for precise control of the flow. The crude oil emerges and is sent to a processing facility where it is separated from natural gas, water, sand, and other impurities. This often happens right at the well site. The separation is a fascinating process. The mixture enters a large sealed vessel where gravity takes over. The lighter gas rises to the top while heavy water and sediment sink to the bottom. Sometimes, water is trapped in the oil as a microscopic emulsion, which is harder to separate. In this case, chemical de-emulsifiers are added to break it down. To maintain pressure in an aging reservoir, secondary recovery methods are used. Water or gas is injected into the formation through other wells to push the remaining oil towards the production well. These techniques can allow up to 60% of a reservoir's oil to be recovered. The average modern well in the U.S. produces between 500 and 1,500 barrels per day. A single barrel is 159 liters. Multiply that across thousands of wells and you begin to grasp the true scale of this global operation. Crude oil itself is a complex cocktail of hundreds of different hydrocarbons. To turn it into petrol, it must undergo a series of technically demanding stages at a refinery. It all starts with fractional distillation. The crude oil is heated to between 350 and 400 degrees Celsius and fed into a tall distillation column. The various components of the oil vaporize and rise to different heights inside the column before they cool, condense, and are drawn off. The petrol fraction is one of the lightest, and it's typically collected at a temperature between 40 and 200 degrees. But this initial distillation only yields about 15 to 20% petrol. To increase the yield, a process called cracking is used. This breaks down long, heavy hydrocarbon molecules into shorter, more valuable ones. The most common method is fluid catalytic cracking, where heavy fractions are heated to nearly 1,000 degrees in the presence of a catalyst. This allows for a much higher yield of petrol from the heavier residues. Hydrocracking, which uses hydrogen under high pressure, is also used. Ultimately, the petrol yield from a single ton of crude oil can be pushed as high as 40 or 50%. The petrol produced so far, however, has a low octane rating. To fix this, it undergoes reforming, a process that restructures the molecules at high temperatures using a platinum catalyst. In the final stage, additives are blended into the petrol to improve its properties: anti-corrosion agents, anti-knock compounds, and detergents. This ensures engine longevity, reduces harmful emissions, and improves efficiency. A single modern refinery can process up to 400,000 barrels of crude oil every single day. The sheer volume is staggering, especially when you consider that the daily petrol consumption in the U.S. alone is around 1.4 billion liters. A river of ancient life, powering the modern world.
Every day, 120,000 commercial flights take off worldwide. A Boeing 777 weighs 280 tons at landing, an Airbus A380, 575 tons. The moment those wheels hit the runway, all that metal, fuel, and passengers slam into the tires at 185 miles per hour. In a fraction of a second, the tire heats up to nearly 400 degrees Fahrenheit. The load on each one is like stacking dozens of cars on a single piece of rubber. And it doesn't burst. Every flight, every day, 120,000 times. But here's the crazy part. An aircraft tire isn't built to survive just one landing. It has to last at least 200 full cycles before replacement. 200 times at 185 miles per hour. 200 times, hundreds of tons pressing down. And it can't fail, not once. That's not a suggestion. It's an international standard. And without meeting it, a tire doesn't get certified. How is that even possible? What's inside this black shell passengers never see, always tucked behind metal doors? Today, we're going inside an aircraft tire factory. What's in there will completely change how you see landing. Let's start with this. An aircraft tire isn't just a bigger car tire. It's fundamentally different. Take the main landing gear tire on a Boeing 737, the world's most common airliner. Diameter, roughly 50 inches. Weight, anywhere from 220 to 265 pounds. Internal pressure, 200 pounds per square inch. Your car runs at 36 pounds per square inch. An aircraft tire inflates almost 6 times harder. That's why when one fails, rare but real, the explosion is violent enough to damage the airframe. In 2000, exploded tire debris punctured Concorde's wing and triggered the catastrophic Paris disaster. That's the cost of failure. The smoke on landing, that white puff you see in videos, isn't burning rubber. It's a tire accelerating from 0 to 185 miles per hour instantly. Before touchdown, it's stationary. At contact, instant violent spin-up. Friction, heat, smoke. The tire survives. Now, here's where it gets interesting. The tire must be both super strong and super light. Every extra pound means extra fuel every single flight, multiplied by thousands of flights yearly over the aircraft's lifetime. This balance, strength versus weight, defines absolutely everything in manufacturing. Engineers obsess over grams. Weight is money. Weight is physics. Get it wrong and airlines lose millions. The raw materials for aircraft tires aren't the same as truck tires. The main ingredient is natural rubber, not synthetic, natural. That's because it has a unique molecular structure that lets the material deform and bounce back thousands of times without fatigue failure. Synthetics can't handle that stress. Here's the thing. All natural rubber for aviation tires comes from plantations in Malaysia, Indonesia, and Thailand, from rubber trees. A farmer makes an incision in the bark. White sap flows out. Latex. After coagulation, pressing, and drying, you get dense blocks of raw rubber. Those blocks get shipped to Michelin, Goodyear, and Bridgestone factories, the trio making nearly every aircraft tire worldwide. But rubber is just the start. The second key component is nylon cord, special threads thinner than human hair that create the reinforcing skeleton inside the tire. A regular car tire has 4 cord layers, an aircraft tire, 30 to 40. And this is where something transforms plain rubber into an aviation tire. But before we get to manufacturing, here's something most people don't know. Aircraft tires aren't filled with air. They're filled with pure nitrogen. At 40,000 feet, the temperature outside hits minus 76 degrees Fahrenheit. Regular air contains moisture. At that temperature, moisture freezes, pressure jumps unpredictably, and the tire can behave on landing in ways engineers never intended. Nitrogen is dry and thermally stable. That's why it's in every aircraft tire in the world. from a small regional ATR to the massive C5 Galaxy. But nitrogen is the final step. First, you have to build what holds it. Aircraft tire production starts with cord. Nylon threads are woven into fabric, then impregnated with rubber compound. The result is a sheet material, strong, flexible, capable of holding enormous pressure. From these sheets, layer by layer, the tire carcass is assembled by hand, not by robots, because every layer has to be stretched with precise tension, aligned, pressed down, every air bubble removed. One bubble, the size of a coin, and the tire is scrap. The operator works on a spinning drum, like a potter with clay. Only instead of clay, he's handling sheets of rubber cord, layer by layer, 30, 40 layers, each one at a precise angle to the last. This crosshatch pattern creates the strength to hold 280 tons. Building a single tire carcass takes several hours. It's handwork demanding experience. No automated line replicates this precision yet. A skilled builder spends years learning to feel the material. Next, mounting the bead ring. This rigid steel ring locks the tire onto the wheel rim, keeping it from blowing off under 200 pounds per square inch of pressure. It gets wrapped in rubber and fused into the carcass on both sides. Then the blank goes into the press mold. Vulcanization begins. Under pressure and 340 degrees Fahrenheit, rubber's molecular chains cross-link, forming a three-dimensional lattice structure. That gives the rubber its elasticity and shape memory. The tire stays 10 to 20 hours under these conditions. That's not a typo, up to 20 hours per unit. While it's in the oven, nothing can be undone. If there's a mistake, they'll only find out at inspection. Every aviation tire goes through multiple inspection levels before shipping. First, visual. A specialist with a magnifying glass examines every inch of the surface, looking for cracks, bumps, foreign contaminants. But the real inspection is invisible. X-ray imaging. Every tire gets scanned, like airport luggage, only far more powerful. The image reveals everything: how cord layers sit, where steel rings are positioned, and whether there are any air pockets inside. Even one bubble larger than allowable size, the tire gets scrapped. No exceptions. Next, ultrasonic scanning. Sensors sweep the entire surface, detecting material delamination the X-ray might miss. Every millimeter, automatically. Results get recorded in that tire's passport. Finally, dynamic testing. The tire gets inflated to working pressure and spun on a test rig, simulating landing loads. Only after passing all three levels does a tire receive its certificate and serial number. Every tire is fully traceable: manufacturer, date, raw material batch, assembler's name. If something goes wrong, they'll find the source within hours. Ever wonder why tire-related aviation incidents are single-digit cases per billion landings? That's why. Because the cost of failure isn't a warranty claim or lawsuit. It's catastrophe. Every year, the world produces about 1.5 million aircraft tires. Michelin controls roughly 60% of that market. A single tire costs $1,500 to $5,000, depending on aircraft type. Airlines replace tires every 200 landings, or sooner if wear becomes critical. But they don't throw them away. They retread them, cut new grooves, re-vulcanize the rubber, run full quality control again. One tire can go through 3 or 4 retreading cycles before it's finally recycled. That tire under your plane may have already survived several hundred landings and still passed every inspection. Next time your plane touches down and you feel that thump and rubber squeal, you'll know exactly what just happened. Hundreds of tons of metal and people entrusted to 4 pieces of rubber. Rubber that dozens of engineers designed, operators assembled by hand, X-rayed, tested with ultrasound, and ran on test rigs. Rubber that in decades has almost never failed. 120,000 times a day, every day. Subscribe to the channel. This is where we go behind doors that are usually closed.
Every year, the world produces billions of square feet of veneer, a petal-thin material hiding the strength and beauty of entire forests. Picture this. From a single log, you can get enough surface area to cover a football field. That's exactly why this industry is worth over $40 billion annually. From one perfect American walnut log, about 3 feet in diameter, you get anywhere from 10,000 to 30,000 square feet of unique surface. One log, almost an entire football field of veneer. Using veneer cuts the need to harvest valuable tree species by 98% compared to making furniture from solid wood. Instead of cutting down 20 trees to make 20 tables, you can harvest one perfect tree and leave the other 19 growing in the forest. But what's behind that number? How does an ordinary tree go through spa treatments, fiery tunnels, and encounters with scalpel-sharp blades to become luxury furniture? Watch closely. At the end, you'll discover a secret almost nobody realizes. Picture a lumber mill that specializes in veneer production. Massive logs of premium hardwoods, oak, ash, maple, walnut, cherry, arrive here by truck. But not every tree makes the cut. These have to be perfectly straight, tall trees with large trunk diameters, and most importantly, free of knots, cracks, and other defects for a significant height. Every knot is a scar that ruins the perfect grain pattern. That's why only the finest specimens are chosen for a veneer. When one of these perfect logs arrives at the mill, it doesn't go straight to the blade. First, it gets the industrial spa treatment. The logs are submerged in enormous pools of hot water or placed in special chambers filled with hot steam. This isn't about cleanliness. This process, lasting anywhere from several hours to several days, at temperatures around 212 degrees Fahrenheit, does two crucial things. It softens the wood, making it more pliable and cooperative for cutting, and it transforms its color, making it richer and more uniform. After the hot bath, the bark gets stripped from the log. A special machine peels away the rough outer shell, revealing clean wood underneath. And now comes the most critical moment before the main show, centering. The log gets locked into the machine, and an operator uses lasers to find its perfect axis of rotation. This is absolutely crucial. Giant pencil in a giant sharpener. The log starts spinning around its axis, and the blade cuts into the spinning wood and starts shaving off a continuous wide ribbon of veneer, just 1/50th to 1/8 of an inch thick. It's like unrolling a paper towel roll. An endless, wet, flexible sheet comes out of the machine, which is then cut into pieces of the right size. This method is highly productive, but it creates a characteristic chaotic pattern that isn't always valued in high-end furniture. The second method, used to obtain the most beautiful decorative veneer, is called slicing. This isn't a sharpener anymore. It's the world's biggest cheese slicer. Here, a log, or part of it cut into beams, is firmly secured to a movable platform. Above it, or to the side, sits a massive, sharp blade. The platform with the wood moves back and forth, or up and down, and with each pass, the blade shaves off a single, perfectly flat sheet of veneer. It's a slower, less productive process, but it's what gives you that refined, linear, or figured grain pattern we value so much in expensive furniture. Depending on exactly how the log was cut before slicing, you can get different types of patterns, radial, tangential, mimicking the look of solid plank. Freshly cut veneer, no matter the method, is called green. It's soaking wet, flexible like damp paper, and tears easily. It needs to dry. The ribbons or sheets of veneer are carefully fed into a long drying chamber. Think of it as a giant tunnel oven, where the veneer slowly moves along on rollers or a mesh conveyor. Hot air circulates inside, gently and evenly pulling moisture out. The process is tightly controlled. Dry it too fast and the veneer will crack or buckle. Within minutes, that wet, floppy sheet becomes dry, slightly brittle but stable. After drying, the veneer sheets have ragged edges. They're stacked high and sent under a massive guillotine. A sharp blade slams down and in one stroke slices off the rough bits, creating perfectly straight edges. Now the sheets are ready for the most critical stage, where it's not machines doing the work, it's people with trained eyes. This is sorting. Specialists carefully inspect each sheet, evaluating its color, grain pattern, and any defects, then sort them into bundles by grade. It's meticulous work because this determines the veneer's price and application. But individual veneer sheets are often too narrow for making something like a tabletop, so they need to be joined into one large panel. This process is called stitching or splicing. Two sheets with perfectly straight edges are fed into a special machine. It presses them tightly together, and a specialized mechanism bonds them. This could be a thin zigzag line of adhesive or a glued paper tape. The result? A large, continuous veneer sheet, ready to be applied to a substrate. Now for some history. Using thin layers of wood goes back thousands of years. Ancient Egyptians used veneer to decorate sarcophagi and furniture 3,000 years ago. But modern industrial veneer production only began in the 19th century with the invention of steam engines and precision machinery. The first veneer peeling lathes appeared in the mid-19th century and revolutionized the furniture industry. Instead of sawing valuable wood species into thick boards and losing most of the material to sawdust, manufacturers could now obtain ultra-thin sheets, maximizing every inch of the log. The global veneer market is a massive industry, turning over more than $40 billion a year. The largest producers are China, the US, Germany, Italy, and Indonesia. Veneer isn't just for furniture. It's used in making doors, musical instruments, yacht interiors, luxury car interiors, and premium space finishes. But the most important application is plywood. Yes, ordinary plywood as we know it is multiple layers of veneer glued together with perpendicular grain direction. This exact structure gives plywood its strength and resistance to warping. And now the most impressive number behind veneer, its efficiency rating. Take one massive, perfectly straight log of premium American walnut, several yards long and about 3 feet across. If you just sawed it into boards, you could make, say, one big table and a few chairs. Now here's the kicker. If you slice that same log into veneer just 24 thousandths of an inch thick, you can get anywhere from 10,000 to 30,000 square feet of unique surface. To put that in perspective, that's enough to cover almost an entire football field from a single log. Using veneer cuts the need to harvest precious hardwoods by 98% compared to making solid wood furniture. Meaning instead of cutting down 20 trees to build 20 tables, we can harvest one perfect tree and leave the other 19 growing in the forest. This makes veneer one of the most environmentally responsible ways to use wood. But veneer has another hidden advantage that few people think about. The thing is, the most beautiful, unique wood grain patterns are often found in the most unusual parts of a tree, where the trunk branches out, in burls, in the root section. If you saw a tree like that into boards, these areas often end up as scrap because they're too small or irregularly shaped. But with veneer production, even a small section with a unique pattern can be turned into several square meters of luxurious material. There are entire categories of exclusive veneer made from burls, wood growths with incredibly complex, swirling patterns. One burl the size of a soccer ball can yield enough veneer to finish an entire study, and this veneer can cost thousands of dollars per square meter. There's even a market for archive veneer, material made from trees cut down decades or even centuries ago and stored in warehouses. Some species of wood that are now protected or extinct can only be found in the form of this archive veneer.
Veneer manufacturing technology is constantly evolving. Modern machines are equipped with laser scanning systems that analyze the log structure before cutting and select the optimal angle and method to produce the most beautiful grain pattern. Computer control allows sheets less than half a millimeter thick to be sliced with precision down to hundredths of an inch. New processing methods are being developed that enable veneer to be stained, embossed with textures, and made to imitate rare species. And so, after journeying from a majestic tree in the forest through a hot bath at 200 degrees Fahrenheit, past a knife sharp as a scalpel, and through the fiery tunnel of a dryer, this material emerges, thin as a petal, carrying all the beauty, history, and unique character of the forest, ready to bring a piece of it into our homes. These billions of dollars aren't just money, they're proof that beauty and practicality can walk hand in hand, allowing us to enjoy nature's unique patterns without causing irreparable harm. Every sheet of veneer is a thin slice of a tree's history, one that lived for decades or centuries and is now ready to serve humanity for centuries more in the form of beautiful furniture.
Imagine a substance that doesn't melt, leaves not a single drop of water, and simply vanishes into thin air. It can freeze anything within seconds, create thick white fog that rolls across the ground, and even stop life itself if handled carelessly. Dry ice isn't just cold, it's a controlled force of nature that humans have learned to harness. Deep beneath the hum of compressors and swirling clouds of white vapor lies a process that seems like magic, where gas transforms into solid matter at -78 degrees. But where does this gas come from on an industrial scale? And why is dry ice production considered a genuine environmental miracle? Watch until the end and you'll see how something so cold can become one of the hottest businesses in the world. Industrial dry ice is nothing other than solid carbon dioxide, which freezes at the extreme temperature of -78.5 degrees Celsius. Put simply, it's the very same carbon dioxide we exhale with every breath, which plants absorb and which gives fizz to your favorite carbonated drinks. Unlike ordinary ice, which melts into water, dry ice possesses a remarkable property: sublimation. It transitions from solid state directly to gas, bypassing the liquid phase entirely. That's why it's dry. It leaves no puddles behind, simply disappearing into invisible gas. This unique ability to cool instantly and evaporate without trace has made it indispensable across dozens of industries. In medicine, dry ice is a genuine guardian of life. It's used for transporting vaccines, donor organs, and blood, where every second's delay and every extra degree could cost a life. In cryotherapy, it's applied for targeted freezing and removal of warts. In the food industry, it's become a guarantor of freshness. Frozen products, meat, and ice cream are transported in containers filled with this cold wonder. And in the world of entertainment, dry ice is the chief instrument for creating magic. The thick, heavy fog rolling across stages at concerts and theatrical performances, or smoking cocktails in bars, all of this is the work of dry ice, which creates impressive visual effects when it contacts hot water. Dry ice production takes place at cryogenic plants. These facilities occupy enormous industrial areas, comparable to several football pitches. At the center of the site stand gigantic cryogenic tanks, steel towers up to 50 feet high, capable of holding up to 100 tons of liquid carbon dioxide. Inside the workshops, there's a constant hum, powerful compressors and hydraulic presses at work. From the giant tanks, liquefied gas flows through thick, frost-covered pipes into the very heart of production, the pressing installations. These machines are absolute monsters, capable of compressing up to 500 kilograms of dry ice in a single minute. When liquid carbon dioxide under enormous pressure bursts from the nozzle into a chamber at normal atmospheric pressure, rapid expansion occurs. This process, known as the Joule-Thomson effect, causes the gas to cool and freeze instantly, transforming into loose, snow-like dry ice. A cloud of thick white vapor rises above the pressing chambers as powerful hydraulic presses, with force measuring hundreds of tons, compress this snow into dense, heavy briquettes or fine pellets. Conveyor belts move continuously, carrying away the icy blocks. They pass through refrigerated tunnels where temperature is kept below -40 degrees. Automated machines slice large slabs into smaller pieces or transform them into pellets the size of peas. Packaging machines work at lightning speed. Precisely calculated quantities of dry ice are poured into special polystyrene thermal containers, from small 1-kilogram packets to enormous containers holding hundreds of kilograms. Automatic sealers hermetically close the packages to slow the sublimation process. In 1 hour, a single such plant can produce about 5 tons of product. Now imagine the working conditions in this frozen kingdom. In zones where presses and packaging lines operate, temperature stays below -40 degrees. Workers here resemble polar explorers. They're dressed in multi-layered thermal insulation suits, wearing special gloves on their hands, since direct contact with dry ice causes instant and extremely painful burns. On their faces are protective goggles and masks, as high concentrations of carbon dioxide in the air can cause dizziness and suffocation. Because of this, powerful ventilation systems must operate in the premises, constantly refreshing the air and maintaining safe oxygen levels. To avoid hypothermia, workers labor in short shifts, alternating work in cold zones with breaks in warm restrooms. Many processes are maximally automated to reduce human presence in extreme conditions. But even with such protection, work at these plants demands incredible endurance and the strictest adherence to safety procedures. So where do plants obtain carbon dioxide in such colossal quantities? The secret is that they don't produce it specially, they collect it. It's a byproduct of other major industrial processes. The main sources are ammonia and fertilizer plants, breweries where gas forms during fermentation, as well as petroleum refining and cement works. Rather than releasing this carbon dioxide into the atmosphere, it's captured by special installations. The gas then undergoes multi-stage purification from impurities, is dried and compressed under high pressure, transitioning to liquid state. This process is the brightest example of industrial symbiosis and circular economy, where waste from one production becomes valuable raw material for another. But for all its usefulness, dry ice is a substance requiring extreme caution. Its temperature is so low that it can cause serious burns upon contact with skin. But the main danger lies in its sublimation. Whilst evaporating, dry ice displaces oxygen from enclosed spaces. Being in an unventilated room where large quantities of dry ice are evaporating can lead to suffocation. Tragic cases are known where people suffered fatal poisoning using dry ice to create fog and enclosed swimming pools. Therefore, working with it requires strict adherence to safety rules, good ventilation, use of protective gloves and goggles. Now let's glimpse into the future, because dry ice has an incredibly exciting one ahead. Right now, scientists and engineers are developing technologies where dry ice plays a key role. For example, in fire suppression. Unlike water or foam, dry ice doesn't conduct electricity and leaves no traces, making it ideal for extinguishing fires in server rooms, museums, or power stations. Dry ice pellets are sprayed onto fire, instantly cooling it and displacing oxygen. Another direction is cryogenic cleaning or blasting. Tiny dry ice pellets are fired under high pressure at contaminated surfaces. Striking them, they instantly evaporate, and the micro-explosion caused by rapid gas expansion literally blasts off dirt, paint, or rust without damaging the surface itself. But the most fantastic prospect is terraforming planets. Scientists are seriously considering the possibility of using carbon dioxide, which in solid form covers Mars's polar caps, to create an atmosphere. By melting Martian dry ice using nuclear explosions or gigantic mirrors, one could trigger a greenhouse effect that would warm the planet and make it habitable. So this cold, smoking material that we use today for cooling drinks might one day become the key to transforming the red planet into our second home. This proves that even the most ordinary-seeming substances conceal within them boundless potential that humanity has yet to unlock.
What you're witnessing here is something that would have made our grandfathers stop dead in their tracks and stare in absolute wonder. This is the forging of a massive rolling mill shaft for a steel plant weighing 5,700 pounds. That's almost 3 tons of solid steel being shaped by pure force and principles that are centuries old. The process starts with a massive steel ingot that's been heated in a gas furnace to around 2,200 degrees Fahrenheit, hot enough to glow like a miniature sun. Back in the days when American steel mills dotted the landscape from Pittsburgh to Gary, Indiana, this kind of work was the backbone of our industrial might. The forging press you're seeing here is a modern hydraulic giant capable of exerting thousands of tons of pressure. But the fundamental process hasn't changed since blacksmiths were shoeing horses on Main Street. Watch closely as the glowing workpiece gets positioned under the press. The operators, and these folks are true craftsmen, use overhead cranes and manipulators to rotate and position the workpiece with incredible precision. Every press strike, every controlled squeeze is carefully calculated. They're not just hammering hot metal, they're restructuring the grain structure of the steel, eliminating internal voids and creating a component that'll eventually face enormous forces in the rolling mill. The shaft gets worked from multiple angles, gradually taking shape. Between each pressing operation, the team repositions the workpiece, sometimes returning it to the furnace to maintain that critical working temperature. This dance between heat and pressure goes on for hours. The hydraulic press moves with deliberate force, almost gently despite its massive power. Around 5,000 to 10,000 tons of pressure compacts the steel's crystalline structure into something far stronger than the original ingot could ever be. What's fascinating is how this forged shaft will serve in a steel mill, helping shape other steel products. It's a beautiful cycle. Metal processing metal, and these shafts can last for years under extreme conditions. Today's technology, precise temperature control, computer-controlled press cycles, metallurgical analysis, ensures consistency our ancestors could only dream of. But the soul of the process remains unchanged: heat, pressure, and the skilled hands of craftsmen who understand steel like old friends. Now here's something that combines brute force with surprising delicacy: the process of coiling a 2-inch spring bar. If you've ever wondered how these massive industrial springs are made, the ones that control freight train suspension or support heavy machinery, you're about to get a lesson. The process starts with raw stock, in this case a solid 2-inch diameter rod of heat-treated spring steel. This isn't ordinary metal. It's been precisely engineered to have the exact balance of hardness and flexibility. Too hard, and it'll snap like a pretzel. Too soft, and it won't spring back properly. Watch as the rod feeds into the coiling machine. The machine grabs one end, while a massive rotating mandrel, essentially a former, begins bending the rod around its circumference. The force required here is substantial. We're talking about permanently deforming 2-inch steel, which demands hydraulic power in the range of several hundred tons. The mandrel size determines the spring's inner diameter, and precision here is critical. As the coiling progresses, you'll notice how smoothly the rod bends despite its thickness. This is achieved through controlled feed rates and constant pressure. The machine maintains tension while rotating, creating consistent spacing between coils. Back in the 30s and 40s, this kind of work was done by hand with tremendous effort, using heat and mechanical advantage. Modern CNC systems can produce springs with tolerances measured in thousandths of an inch. What you're seeing here is one of the most reliable welding processes ever developed: submerged arc welding. This technique has been joining heavy steel since the 1930s. Here's what makes this process so special. Unlike stick welding, which your grandfather might have done in his garage, or even modern semi-automatic welding, submerged arc welding happens beneath a blanket of granulated flux. This flux, which looks almost like coarse sand, performs several critical functions. It shields the molten weld pool from atmospheric contamination, prevents oxidation, and actually contributes to the chemistry of the weld itself. The setup is mesmerizing. A continuously fed wire electrode runs through the welding head, and when it strikes an arc to the base metal, it melts both the electrode wire and the parent material, creating a deeply penetrating weld. But you can't see any of this happening because it's all taking place under that protective layer of flux. The flux melts on top, forming a protective slag that operators chip off later. Watch the welding head move along the joint. It's typically automated for consistency. The process can deposit weld metal at rates that would make a stick welder cry with envy, 10 to 50 pounds per hour depending on the setup. That's why submerged arc welding is the #1 choice for welding thick sections in shipbuilding, pressure vessel fabrication, and structural steelwork. The beauty of this process lies in its depth of penetration. Submerged arc welding can achieve full penetration welds on steel up to 3/4 of an inch thick in a single pass. Now, let's look at modern hot forging, a process that's adapted traditional forging techniques to produce complex automotive and industrial components at volumes that would have been unthinkable in the old days of small-batch artisanal blacksmithing. The process begins with steel blanks, which are cut to precise lengths and then fed into induction heating systems. Induction heating is one of those technologies that seems almost magical when you first encounter it. No flame, no combustion. But within seconds, a steel blank placed inside an induction coil glows cherry red, then orange, then that brilliant yellow-white that tells you it's ready for forging. Alternating current flowing through the coil creates a rapidly changing magnetic field, which induces electrical currents in the steel itself, and these currents generate heat through resistance. After heating to the optimal forging temperature, typically between 2000 and 2300 degrees Fahrenheit. Depending on the steel grade, the blank is transferred to the forging press. Sophisticated closed die forging is used, where the hot steel is placed between two die halves that contain the negative impression of the desired part. When these dies come together with thousands of tons of force, the steel has nowhere to go but to fill every contour of that cavity. Excess material, called flash, gets squeezed out around the edges and is later trimmed off. What's remarkable is the speed and precision of modern forging presses, machines that can complete a forging cycle in just a few seconds, yet achieve dimensional tolerances that would have required extensive machining in the past. Sometimes you need to bend metal that's so big it seems almost impossible, and that's exactly what a horizontal bending press specializes in, forming massive pipes that can be several feet in diameter. The problem with bending large pipes is avoiding what we call wrinkling on the inside radius and tearing on the outside radius. The system solves this through controlled hydraulic pressure applied by a precisely formed die that supports the pipe during the bending process. Watch as the massive pipe gets positioned in the machine. That positioning alone requires overhead cranes and careful alignment. The bending die, often weighing several tons itself, presses against the pipe while it's supported at both ends. The hydraulic system applies hundreds of tons of force, gradually bending the pipe through the desired angle. Even with pipes this size, the bend radius, angle, and final dimensions can be controlled to surprisingly tight tolerances. These bent pipes end up in industrial piping systems, structural applications, and even shipbuilding. We're watching the cutting of a heavy railroad rail, 47 kilograms per meter, which translates to roughly 95 pounds per yard, using oxy-fuel cutting with propane. The oxy-propane torch system operates on a principle that's elegantly simple, yet demands real skill to execute properly. The propane flame, mixed with oxygen in the torch's preheat nozzles, heats a spot on the steel to ignition temperature, around 1600 degrees Fahrenheit for steel. Once that critical temperature is reached, a stream of pure oxygen under high pressure is introduced through the cutting nozzle. Here's the beautiful part. The oxygen doesn't melt the steel, it actually oxidizes it. The steel burns in the oxygen stream, and the force of that oxygen jet blows the molten iron oxide out of the cut, creating the kerf. The operator maintains a specific distance from the workpiece, the gap between the torch tip and the work surface, typically around 1/8 to 1/4 inch. Too close, and the tip will clog with splatter. Too far, and the cut becomes ragged. For cutting rail, you'll notice the torch follows the rail's profile. The rail has this characteristic mushroom shape: wide base, narrow web, and heavy head on top. Each section has different thickness, so cutting speed must be adjusted accordingly. We're now entering the realm of precision machining, where tolerances are measured in 10,000ths of an inch, and programming is just as critical as the actual technique. What you're witnessing is CNC milling of optical chuck jaws, programmed using CAM software, and this represents the perfect marriage of computer manufacturing and skilled craftsmanship. The process begins in the CAM software. A programmer working from engineering drawings creates a three-dimensional model of the chuck jaw, then generates the tool paths that will machine it. The program calculates optimal cutting strategies, selecting appropriate tools, determining feed rates and spindle speeds, and simulating the entire process virtually to catch any potential collisions or errors before a single chip is cut. Watch the CNC mill executing these programmed tool paths. This is likely a high-precision vertical machining center, equipped with a spindle that can rotate at 10,000 RPM or more while maintaining accuracy. Instead of plunging straight down, the tool follows spiral and trochoidal paths that maintain constant chip load and reduce tool wear. Notice the surface finish developing on the chuck jaw faces. These are critical contact surfaces that will grip workpieces, and they must be flat within microns and properly finished to avoid damaging delicate components. The float glass process you're watching, one of those manufacturing breakthroughs that completely transformed the industry. And remarkably, the core principle hasn't changed since it was invented back in the 1950s. Here's how this incredible process works. Molten glass, heated to around 2000 degrees Fahrenheit, flows continuously from the furnace onto the surface of a molten tin bath. The glass literally floats on the tin, spreading under gravity and surface tension, forming a ribbon with parallel surfaces and uniform thickness. Watch as the glass ribbon advances through the tin bath. Temperature is carefully controlled, gradually cooling as the glass moves forward. This controlled cooling, called annealing, is critical. It relieves internal stresses that would otherwise cause the glass to crack or shatter during cutting or installation. As the glass exits the tin bath, it's cool enough to be supported by rollers entering what's called a layer, a long cooling tunnel where temperature continues to drop under precise control. The glass emerges at room temperature, perfectly flat with optical clarity that would have been impossible to achieve consistently using the old methods of sheet glass production. The production line can create thousands of square feet of glass daily, all with consistent quality. The ribbon is then cut to size, inspected, and prepared for further processing like tempering or coating.
A poisonous metal that saves lives. Sounds paradoxical, but it's true. Lead, one of the most toxic elements on Earth. It poisoned Roman emperors, killed thousands of workers, got banned from paint and gasoline. But without it, not a single car on the planet would start. Every second, the world produces 2 tons of lead. 85% goes into batteries, the heart of every vehicle. Lead shields doctors from X-rays and stops radiation at nuclear plants. The heaviest common metal you can hold in your hands, 11 grams per cubic centimeter. How do you get a bluish metal that kills and saves at the same time from silver ore? You'll find out why the Roman Empire fell because of lead pipes, how a lead-acid battery works, and why this ancient poison is still irreplaceable today. Watch till the end. The finale reveals the dark side of progress. This is the story of a metal humanity can neither embrace nor let go.
Lead's story begins deep in ancient times. About 7,000 years ago, people learned to smelt lead from ore. It was one of the first metals humans extracted from stone. Lead melts at a low temperature, just 627 degrees Fahrenheit. Even a campfire can melt lead ore. The ancient Egyptians used lead to make statuettes and cosmetics. Yes, women lined their eyes with lead-based white paint. The Roman Empire took lead use to absurd levels. Lead water pipes stretched throughout Rome. Wine was stored in lead amphorae. The metal made the drink sweeter. Wealthy Romans ate from lead dishes. Aristocracy sweetened wine with lead sugar, lead acetate, which actually tastes sweet. The result? Mass poisonings. Roman nobility suffered from gout, insanity, infertility. Many historians believe lead poisoning of the elite became one of the causes of Rome's fall. Emperor Nero, known for his madness, may have been poisoned by lead since childhood. In the Middle Ages, lead was used to make cathedral roofs, stained glass windows, and printing type. Alchemists considered lead the basest of metals and tried to turn it into gold. The 19th century brought a boom in the lead industry.
Lead white became the foundation for paints. Bright, durable, cheap. Lead coated toys, furniture, house walls. Children gnawed on lead toys and died from poisoning. Workers at lead plants perished by the dozens. Metal dust destroyed their nervous systems. In the 20th century, lead was added to gasoline as an anti-knock additive. Tetraethyl lead boosted octane ratings. Engines ran smoother. But exhaust fumes poisoned cities. By century's end, leaded gasoline was banned almost everywhere. Lead paints were banned too. Lead pipes replaced with plastic. It seemed the age of lead was over. But no, lead production kept growing because a new massive application emerged: car batteries.
Where does lead come from today? The primary lead mineral is galena, lead sulfide, cube-shaped crystals, silvery gray with a metallic luster, extremely heavy, density of about 0.27 pounds per cubic inch. Galena often occurs alongside silver, zinc, copper. The largest deposits are found in China, Australia, the USA, Peru, Mexico. China produces half the world's lead, around 6 million tons per year. Lead is extracted through open-pit mining in quarries or underground mines. They blast the rock, crush it, grind it. The result is ore containing 3 to 10% lead. That's enough for industrial processing. The ore is enriched through flotation. Crushed ore is mixed with water and special reagents. Galena particles stick to air bubbles and float up, forming foam. Waste rock gets washed away. The concentrate contains up to 70.
Lead concentrate gets roasted in massive furnaces at around 1800 degrees Fahrenheit. Lead sulfide transforms into lead oxide, releasing sulfur dioxide gas. They capture this gas and use it to make sulfuric acid. Nothing goes to waste. Lead oxide gets mixed with coke and fluxes, limestone or quartz. Load it into a shaft furnace. Hot air blasts in from below. Temperature climbs to 2200 degrees. Carbon reduces the lead oxide back to metal. Molten lead pools at the bottom of the furnace, a heavy gray-blue liquid. Lead is 11 times denser than water. Drop a steel ball into molten lead and it'll float right on the surface. They tap the melt from the furnace into ladles. The melt's still impure, contains copper, zinc, silver, gold. Yeah, lead ore often carries precious metals. Extracting them pays for part of production. Lead gets refined, purified. Heat it to 900 degrees and add zinc. Silver and gold dissolve in the zinc and float up. They skim them off.
The purified lead gets poured into ingots. A standard ingot weighs about 55 pounds and is the size of a brick, but it weighs like a bag of cement. Try lifting it. Lead is heavy and soft. You can cut it with a knife, scratch it with your fingernail. At room temperature, lead develops a dull oxide film, loses its shine. A fresh cut is silvery blue, beautiful, but goes dull within a minute. Lead doesn't rust in the usual sense. The oxide film protects the metal from further corrosion. That's why Roman lead pipes have survived 2,000 years. But the key property of lead is its toxicity. Lead and its compounds are poisonous. Once it enters the body, lead accumulates in bones, replacing calcium. It destroys the nervous system, causes anemia, damages kidneys and brain. Especially dangerous for children. Even tiny doses disrupt nervous system development. There is no safe level of lead in blood. Any amount is harmful. That's why working with lead demands the strictest safety measures: respirators, protective clothing, showers after every shift.
But if lead is so toxic, why do they keep producing it in such massive quantities? Because lead has properties that simply can't be replaced. First, its weight. Lead is 1.5 times heavier than iron. Second, it's soft and easy to work with. Third, it blocks radiation. Gamma rays and X-rays are absorbed by lead better than any other affordable metal. Only gold and tungsten are better, but they're way too expensive. So lead gets used for radiation protection. X-ray room walls are lined with lead sheets. Doctors and technicians wear lead aprons, weigh about 10 pounds, uncomfortable, but they protect. Containers for transporting radioactive materials are made from lead several inches thick. At nuclear power plants, lead is used in shielding systems. Viewing windows for observing reactors are made from leaded glass, transparent, but contains up to 70% lead oxide. This glass stops radiation while letting light through. Without lead, nuclear medicine and power wouldn't be possible. But the main use of lead? Batteries. 85% of global lead production goes into lead-acid batteries. These are the most common type of battery on the planet. Every car with an internal combustion engine has one. 1 billion cars means 1 billion lead batteries. How does it work? Inside a plastic case, there are plates made of lead and lead dioxide submerged in sulfuric acid. During discharge, the lead and lead dioxide react with the acid, forming lead sulfate and water. Electrical energy is released. During charging, the process reverses. Electricity converts the lead sulfate back into metal and dioxide. This cycle can repeat hundreds of times. Lead-acid batteries are reliable, cheap, and can handle high currents. Perfect for starting an engine. A starter motor draws hundreds of amps. Lithium-ion batteries can't compete in this application yet. One car battery contains between 22 and 33 pounds of lead. It lasts 3 to 5 years, then gets recycled. Lead is the recycling champion among all materials. Up to 99% of lead from old batteries makes it back into production. An old battery gets dropped off at a collection point where it's disassembled and crushed. Lead plates are melted down, purified, and cast into ingots. A new battery contains up to 80% recycled lead. This makes economic sense. Secondary lead costs less than primary. And it's environmentally sound. No need to dig new mines. Global lead production runs about 12 million tons per year. Roughly half comes from recycled material. Lead prices hover around $2,000 per ton, cheap compared to other metals. Beyond batteries and radiation shielding, lead shows up in cable sheathing, ammunition, fishing weights, and wheel balancing weights, in construction for soundproofing and waterproofing. But these uses are gradually declining as manufacturers hunt for less toxic alternatives. Lead's future lies in batteries and radiation protection. Until someone invents a replacement, lead remains irreplaceable.
And just like that, traveling from silvery galena crystals through the inferno of furnaces at 1200 degrees and complex purification from impurities, lead emerges, the most contradictory metal in human history. A metal that poisoned Roman emperors and saves lives in hospitals. Banned in paints and toys, yet no car starts without it.